or good day for those who are across the ocean, I don't know. So I'm Sylvie Bensoni, the director of this Institute, Henri Poincaré, and I'm very pleased to welcome you today, despite the conditions. And it's the start of a new program. We are very happy that we can hold it, even though it's not the optimal conditions. And I would like to show you a little bit about the Institute and the team who is working for this program to run as smoothly as possible, and in particular this workshop this week. So the whole program is entitled, if I'm not confused, Mathematical Modeling of Organization in Living Matter. And it has been organized by a team of the Institute called Centre Émile Borel. The history of this program is that it was submitted as a pre-proposal in 2018 and then accepted by the scientific board in 2019. We have here in the room, I'm not sure, Sylvie Lermite, who is the program manager. No, she's just, yeah. And Delphine Lépicier, who is the assistant of this program. And the scientific organizers, we have two of them here. And maybe some others in the room, I don't know. Sorry. So thank you for submitting this program, and I hope it will be successful as you hope it. Just a few words about the Institute. So I don't know if you know it, but it was founded in 1928 to foster scientific interaction between French mathematicians and physicists and those from abroad, and it's devoted to research, but also to training, and more recently, I would say in the last decade, it has been running some outreach activities, and now we have a very exciting perspective, which is the opening of the building, the opposite building, a building built by Jean Perrin, and in particular, it will host a museum, a math museum called Maison Poincaré. And I would also like to mention, in case you are not aware, last year, just 1 year ago, we had a program which was in some sense connected to yours. So if you're not aware of it, maybe you can check the website of this program, which was organized, I don't remember, yes, by Anne-Florence Bitbol, Claude Lauverdeau, Mikhail Tikhonov, and Alexandra Valzac. We have a number of partners. So the big partner is called Carmin. It's a kind of strange thing. It's a laboratoire d'excellence, which gathers not only the Institute, but also the CIMPA, so the Centre International de Mathématiques Pures et Appliquées, which runs some programs in developing countries, CERM in Lumini, that I guess you know, and IHES in Bure-sur-Yvette. And we also have an endowment fund, and we have support, in particular for this program, from the Fondation Sciences Mathématiques de Paris. And I would like to mention that we have just launched a platform, which is called Carmin TV, which is supposed to gather all the videos that are recorded in our institutes. In particular, it should have the videos that are being recorded in this program, this very program. So I encourage you very much to visit this platform and browse it to find whatever you like. So just if you are, for those who are here, you have just seen the cafeteria, the newly refurbished cafeteria. Those abroad will experience it later. And also there is the how is it called? On the second floor for the researchers, there is this space where you can interact. So now we have a team which is not limited to Centre Émile Borel. We are, the director, so Dominique Moana, the deputy director, is here in the room. Aurore Marcos, our secretary general, she's working from home today, as well as Émilie Faure, our assistant. There is the team from Centre Émile Borel, so maybe you have met just when you arrived Sylvie Lermite and Delphine Lépicier, but there is also Absadia and Florence da Silva who are working from home today. The finance office, they are here. Two of them are here, back in the room, so maybe, I don't know if you want to come. So So this is Elodie and Anne-Marie, who are working in the finance office. And I suppose that those of whom who are supported, who have some financial support, they will have to do with these two ladies. So Elodie and Anne-Marie, thank you. So Elodie and Anne-Marie Lundi. And their office is on the 3rd floor. Thank you. And from the Maison Poincaré, which is not only a future museum, but also a department devoted to outreach activities, we have a newly appointed manager who is Elodie Chiroux, but I don't see her here, and Adrien Rossi, who is a science communicator. And in the library, so I can see Naya, if you want to just come by. So the manager from the library is called Naya, and she's working with Henri and Antoine in the library. You also have met some people from the reception office, maybe Eric, I don't have his picture, Florence, I don't have her picture either, and Sylvie and Patricia. And finally, there is a multimedia office, which is in charge of the IT and the audiovisual issues, with Jeff, Enzo, and Cécile. I can't see her here, but okay. So all these people might have occasions to interact with you, so don't be surprised that we are so many people here. And of course, since we're at the beginning of the year, I dare wishing you a happy new year, hoping that you'll be better afterwards than now. And I wish you, of course, a successful program, in particular a successful workshop this week. So thank you and enjoy.
So thank you, Sylvie, for this presentation of this beautiful institute, which will host us for the week and for those who stay for the trimester for 2 or 3 months. The organization of this workshop was organized by the closest is Luis Almeida, who is here. I am Benoît Pertam. Tommaso Lorenzi, who is on the second row here and coming from Torino. Chloé Audebert is not yet here. She will be a little bit later. She is late. And Thomas Lepoutre stays at home. He has 2 children and already COVID at home. So he will just follow us from the Zoom link or the YouTube link. Both of them are open, by the way, and they work properly. Most of the people are online. So a few informations for the trimester. So first for the week, first of all, as you have seen, the university allows us to run completely the program. The only restriction is that we cannot have coffee breaks. So we have breaks without coffee. I'm sorry about that, but that's one of the safety rules that they enforce if we want to run the program in the week normally. So we have a shorter break. So we changed the program recently to make a shorter breaks because if there is no coffee, there is no reason to stay a long time outside. For those who will present posters, tomorrow afternoon, the team will display the places for posters. I don't know how it works, by the way, but they will be placed around 2 p.m. And so during the break, you can dispatch your posters outside here. It will be on the side of the at this floor. What else? So another thing is for lunch. So we don't either provide lunch, of course. It's not really a problem. This area is full of restaurants, and I'm sure they will be completely empty. So it's you can find places. So a little bit later, for those, I'm sure most of you know what is around. For those who do not know, they will give a list of restaurants which will be available outside around noon. In any case, if you turn left, you get the Rue Saint-Jacques, which is the street which, if you follow it, goes to Santiago de Compostela. And if you're at the end of the week, maybe if you want to continue, you can do the pilgrim route. And if you turn right, it's a little bit more complicated, but you arrive also to Rue Mouffetard, where you have also as many restaurants as you want. So whatever you do, you will find restaurants in this area. And for those who know Jussieu, there is a cafeteria in Jussieu where you can go. It's open, you don't need any card, no sanitary pass, by the way, it's easier than to come in here. And you can always have lunch there. I think that's all for practical questions. Do I forget something? Just be careful because the staff here, in principle, in France now, the rule is that you should not work. You should work at home. You should not come to work. So the staff agreed to come and run the conference, which is against the rule. So please be careful. Wear your mask as you should wear it, above the nose, below your mouth, and try not to create big groups to keep as much as possible the safety conditions. Okay, I don't think I forgot something. Any questions? Anything I would have forgotten? Anything you want to note about this area? No? Okay, so we will begin. We'll begin with... but I'm not sure. But okay, so what time is it, by the way? So we have... okay, we have 10 more minutes, so we have time to run it correctly. So I propose to wait because people are online. So I propose to wait for the 10 more minutes to begin really on time.
sont entre nous. Eh bien, écoute, j'ai fait une bêtise, j'étais sûr. Donc, je repars aux États-Unis. Et j'avais une conférence la semaine dernière qui venait d'être annulée. Une conférence en Angleterre, là, j'étais certain que
Okay, so I think we will start on time. So for our first talk, we will have the pleasure of listening to Pierre-Emmanuel Jabin from Penn State, who's going to talk about tracking the adaptation and compensation processes of patients' brain arterial network to an evolving glioblastoma. Okay, thank you, Pierre-Emmanuel.
And so I must say it's a very great pleasure to be here. I was actually quite convinced the conference was going to be canceled. It's also a relief after, that's my first in-person conference in well, 2 years, like many of us, and it's really very nice. So what I want to talk about today is something very applied, so you're not going to see a lot of math. And I want to explain a little bit the context of that. This is a collaboration that started when I was still at the University of Maryland with people from the NIH, and in particular around Henri, so the last one here. And Henri's idea was to try to see if we could predict the evolution of glioblastoma, and in particular the evolution to glioblastoma from another type of tumor by looking at the changes in the brain's arterial network. And that has proved, so it's a very natural idea. We're not the only one to have had it, so you'll find other works in a similar spirit. What I'll try to emphasize today are the basic difficulties that you're facing when you're trying to do something like this. All right, so as I said, this is a very natural and a very basic question, right? So your brain has a very well-developed arterial network. And of course, as you know, the brain uses a lot of nutrients, and so it has high metabolic needs, right? So you need the arterial network to provide this. And so that it works, right, that thing must be very extensive, it must be extremely robust, and it has to be adaptive. And in particular, because of this adaptive property, right, what we believe is that if there is a change somewhere in the brain, so a tumor locally, for example, then that should lead to changes everywhere. Because the arterial network should adjust to compensate for the different needs of the various of the regions. And so then we turn to glioblastoma, right, that are a very big topic in brain cancer. Those are the very nasty ones in the sense that you don't really expect to survive them, and the issue is fatal within a few years usually. They also very often do not start at glioblastoma. So you start with another type of brain cancer, one that is more benign, and then at some point it evolves into a glioblastoma, and then it's mostly very bad news. So there's a lot of interest to try to understand them for this reason, and to try to detect them, and detect them as early as possible. So this is basically the question, right? Can we see from changes in the brain arterial network that a benign cancer changed to a glioblastoma, and can we predict what's going to happen, how fast it's going to happen afterwards? Now, of course, I won't be able to answer the question fully, right? I'll just give a few preliminary results here. As you will see, one reason we cannot answer this question fully is lack of data for what we want to do. All right, so this is just a rough idea that there's also different subtypes of glioblastoma, right? And they have very different distribution in the brain, and they behave in a very different manner. So what you see here is an average density, right? So they took MRIs of various patients, right? And looked at where the tumor cells were, and the higher density, so the red, right, indicates where you have high correlations between patients concerning the localization of the tumor. And you see that for some subtypes, it seems to be all over the place, and other subtypes, you have more correlations. All right, so what do we want to do if we want to try to do a study like this? Well, the first thing, and that is the big issue, we need to have high-resolution MRIs of patients' brain. And this is too bad because, as you will find out, the current protocol for brain cancer patients does not ask for high-resolution MRI of patients' brain. So basically, the first thing we need, we won't have it in most cases. That's something, of course, I had no idea of when we started on this, right? This is the kind of things you find out one step after another. We ended up having relatively complete data for one patient. So this is what strongly limits the kind of conclusions that you can draw for this kind of study at the present stage. They do MRI of patients, right? They're just low resolution. And another question will also be, even for that one patient we don't have enough high-resolution MRIs. So the question is, if you have one good high-resolution MRI and plenty of low-resolution MRI, how do you use the low-resolution MRI to still do what you want to do out of all of this? All right. So then what do you need? First of all, there's a lot of image processing. Right? What you need to be able to have is a reasonable software that if you feed it an MRI, right, it will give you back some sort of arterial structure of the brain. Okay. And I'll discuss a little bit what we've done there, right? This is not very hard. It's just extremely time-consuming. And of course, you still want to be able to handle quite a few of those MRIs, right? So you want human intervention, to be as low as possible within this sort of techniques. And the second step that has proved just as frustrating as the others, right, is now we would like to understand what the blood flow is like. Because we believe that changes in the structure of a network, right, they are there because there are changes that are needed for the blood flow. So that's what we want to see. So we need to be able to model the blood flow, given the result of the previous step. And so I'll go slowly over this kind of things. Again, there's no big math here, right? But just tricky modeling. All right. So what type of data did we have available to do all of this? So I said for patients, right? We didn't have a necessarily very good high-resolution MRI or MRA. But we had high-resolution. There are data sets for healthy people with high-resolution MRA that we can use. And so those are typically those first two, right? So we used a study from 2013, right? Around 60 people in it. and mRNA up to 400 micrometers. And then more recent studies, 2017, 2018, right? Just one person, all right? But with a very high resolution mRNA, 150 micrometer. And all of this typically uses motion correction, so it's a fairly heavy type of machinery that you have to put in place, right? With this kind of resolution, you can't have even if you ask people to stay as you know, please don't move your head, right? That's not going to be good enough for this kind of resolution, of course. So, so it's a very, from the technical side, which I know nothing about, I just saw the thing one day, right? It's a pretty expensive equipment. Then the reason we started this is initially so the NIH is a big, so Vous, the National Institute of Health, right? And it's a very nice idea because, for example, you have a very big campus near Washington, and they have a hospital and they have a research center at the same place. So they actually see patients. And so initially, that's what made me hopeful that we would have access to the data and the right type of data. And so indeed, the third data set, right, was a group of 400 patients, which was reasonably optimistic. The problem, as I was saying, is out of this group of 400 people, only one actually had a high-resolution MRI at 400 micrometers. And all the others had only very low images. Now, this is something we found out right in the middle of it. So keep that in mind whenever I'm saying anything. We were not able to actually test the conclusions of this over a large enough group to validate them fully. So that's what we used. So immediately you see the issues, right? You have different data sets. They have different resolutions. They use different parameters from the imaging. They use different equipments, actually. So already putting all of them together is not completely obvious, right? On the actual patients, so on the actual thing that we want to study, we have only very limited data. And in particular, I have one time series MRI on one patient, right? That's it. So as I said, this is essentially a proof of concept at this point, nothing more. All right, so let me describe very, very briefly the software to get an arterial network out of the MRI, right? And there's essentially roughly 5 steps, and I really pushed that we used well-known algorithm for each step instead of trying to do something on our own, which I think was a lot safer. So you need to do the raw image registration first, right, to get to something that you can actually use. Then you want to do a filtering. Then the key step is, of course, the skeletonization. Right? So that's where out of the image you want to get curves. Right? And here we used a very well-known now curve skeletonization algorithm. What you get out of that, there are some disconnected branches. So the algorithm was typically not able to connect everything. So you need a manual error correction step. The way this is done, the algorithm identifies the disconnected branches. So we had a student that was going there, and then the algorithm was showing different branches, and then the student was trying to see if this was an obvious disconnection or not. And branches that we could not connect, we removed. And then you get to a final graph representation after the skeletonization. Right? So the final graph representation, this is what I'm going to show you afterwards. What that means, right, is you need to, the skeletonization will still give you a sort of weird curve, right? So you need to identify its beginning, its end, its length, some measure of curvature as well can be useful, things like this. And so all of this is on GitHub. It's not very user-friendly, as you can imagine, but it's still, you know, you can still go and play with it if you want to. All right. So just a few more words, right, on the vascular filtering. Again, there are a few subsets here. Again, we used a very well-known method, right? So you have a thresholding, which removes a lot of the noise and then things like that. And then this allows to split the image into connected components. And this splitting is very key because then you apply a variational growing technique in each of the component. And you absolutely don't want to do that on the whole thing, otherwise it goes everywhere. But having a very localized region, then the result is not too bad. But initially we just tried to use the variational region growing on the whole thing, and it was a total mess. All right. A few more words as well on the graph representation and a little bit on brain's anatomy. I had no idea about what the arterial network in the brain looks like, right? So I still remember the first meeting, and I show up and I said, well, it should be a graph, right? So right, you have big arteries, they arrive in the brain, and then they split, right? Logical. But it's not like that for a good reason. So in particular, you have something which is called the circle of Willis, which is a circle. Right? So not a graph. So what we do is we take out the circle of Willis, which is the first stage of the arterial network, right? And then we have various graphs from the circle of Willis downwards. And the graph is pretty much what you would expect, right? Each node in the graph is a bifurcation point, so it's where a vessel is splitting or finishing in the sense that we couldn't identify anything further, right? And the edges correspond to the center line of the skeletonization that we had. And as I said, we completely discarded the branches that we couldn't connect to the network. All right. And typically from the circle of Willis, as I said, you're going to have different graphs, right, which we use this kind of initials. If you don't know much about brain anatomy, which is still roughly my case, this is, well, those are just different regions in the brain, and that's it. All right. So here's a little bit of an example of what's going on. All right. So the left, right, is your magnetic resonance image, right, after registration. So this is the sort of stuff that you have, right? And the goal is to end up with what is here. Right. So that's what the software has to do. So, okay, you do segmentation, you identify the center lines, right? You identify the circle of Willis, and here you see that on this patient, the tumor was here, right? You get to something like that. And if you zoom, you have something of this type, okay? And out of that, you can get a graph representation by identifying the terminating nodes, then every bifurcation nodes up, and reconstruct the graph. And on the edges, you can also encode various properties like an estimated length, right? Now, estimated length, you see that those things are not straight, huh? As would be expected. So it's worth what it's worth, right? We even estimated the curvature, which again, it's what it is, right? It's an estimation. But this is what the software is doing, and I'm not spending a lot of time on this. The poor students who were involved in the project did spend a huge amount of time in coding that. And then you can do various statistical analysis over the graph, right? So here we showed, for example, the distribution of the branch length, right? Depending on which graph you had, so which region of the brain, where you start from for the circle of Willis, right? And you see that there are differences, but they are reasonably homogeneous, right? Now, the graph level is a little bit all over the place, right? Which is what you would expect, because you're probably missing a lot of the smaller blood vessels with this sort of things, right? And this also allows us comparison of some of those statistical properties between the various data sets that we've been using, which is useful, again, as a validation point. Here I'm just looking at 3 compartments out of all of them, right? And you see that, of course, the resolution plays a very big role, right? So to remind you, the first data set, the right data set, resolution was 400 micrometers, right? The spec data set is 1 person, but 150 micrometers. And our GBM patient was 400 micrometers again. And so the number of branches, for example, it's very, very telling. Of course, with a better resolution, you have a lot more branches. No surprise there. You see that our GBM patient, however, who had the same resolution as the right data set, it fits reasonably well within the statistical variation of that data set, right? So that was certainly reassuring. Right. So here's the same compartment, right? One patient on the right data set, one the glioblastoma patient, and the one patient from SPEC, right? Just to give you an idea. Again, they are reasonably similar, right? It's not completely crazy. Very, very obviously, they are not identical as well. And this is not a big surprise, by the way. This is probably not only an artifact of the data sets themselves. Doctors don't really expect every one of us to have the exact same arterial network, even from a topological point of view. All right, so this is another compartment, and it's pretty much the same type of conclusion, right? Now, the next thing is they, of course, wanted to do blood flow simulations. And initially, right, as with the rest of that study, I was extremely naive. So I thought, sure, right, we're going to have a good representation of the blood vessels. And then I know plenty of good people who have done, you know, a good fluid structure model. We are going to pick one of those, and there's going to be a lot of work again for the students to implement them, but this is going to work, right? And when I saw the result, it was obviously not going to be working, not like that. So of course, already the modeling is a very complicated business, right? Because blood is not a simple fluid, right? It's non-Newtonian, viscous, especially at the low scales that we are going to be looking at, right? Maybe less viscous at the larger scale, so how do you separate that is already an issue, right? As I said, you need a fluid structure model because the vessel's boundary are not rigid. And the elasticity or the dynamics of the boundary of the blood vessels was shown to play a big role. And all that means that those models are very complex. And if you want to use them, and if you want to solve a 3D flow, you realize that you need a very good geometry. And if the geometry that you have is not even very accurate, right, what you're gaining by using this kind of very complex model is probably very debatable because you have no idea where you are. And of course, the last point is we have a pulse, right? So blood flows are not steady flow. So on top of that, you would have to calculate, I don't know, periodic solutions or something like this. So when we ended up with this kind of representation, right, we had an extensive discussion, but then I realized the initial plan was absolutely not going to work. So then we decided to take a very simplistic model, which is slightly crazy, but fits well with the roughness of a representation that we got. And so I ended up looking at very old engineering textbooks, right, and pipe models. Right, so this was very important, and it's still used very extensively. And it's basically, you know, you have water pipes, right, and they split, and you need to be able to calculate the pressure and the flow at various parts of the pipe. And so you have models like that, and we chose to use what is called as the Hazen-Williams equation. And what this is an estimate of steady flow in a pipe. And in particular, it tells you the loss of pressure from the head of the pipe to the tail of the pipe based on the flow, right, which is Q, the diameter of the pipe, which is D, and its length, which is L. Right? And you have a few parameters there, the roughness coefficient C, right, and what is called the flow exponent K. And as I said, this was initially used for water, but of course you don't need to keep the same coefficients. And now the issue here is it's not clear that this is capturing correctly the viscosity of the flow. All right. However, one advantage of this sort of model is you don't have to use the same coefficients for each part of the arterial network. And so with this idea that the flow is very different in the larger blood vessels versus the smaller blood vessels, right? What we did is we divided the arterial network into compartments, depending on the level of the graph where you were, right? So the estimated diameter of the blood vessel was useful for this, and we used different constants for each compartment. And after that, solving this is a relatively simple linear programming type of things, right? What you end up having is a set of equations from the beginning to the end. You still need to have some sort of estimates, right? Like terminating pressure, for which we really don't have any good measurements, because we know very, very little. So it's still not as easy as it sounds, right? So this is what it looks like, right? You have an equation on each edge of the graph, right? You assume that the pressure is the same on the nodes, right? And then on each edge, right, you have this equation. So you put the continuity of the pressure, right? And of course, you have conservation of the flux, right, at each node. So all the incoming flux are equal to all the outgoing flux. And if you have a graph, right, then this has a unique solution. So provided you know how to resolve, again, the circle of Willis stage, then the rest of it, you can solve that. Right. So this is what our choice of parameters, right? So K was uniform, and then the roughness constant was changed. And as I said, we took 4 compartments, right, depending on the diameter of a radius of each blood vessel. You see that they are not completely different, right, from one to another. And the big issue was choosing the terminating pressures, because again, we basically have no data. And you know, I should say, the more we went into that, the happier I was that we didn't try to do 3D flows from the start, because doing 3D flows without even a terminating pressure, I don't see what we could have done here. All right. So to fit all of that, we used another study by Blanco, which had a detailed arterial network of the whole body, actually. And that was based mostly on existing literature and autopsy. And so they had around 2,000 blood vessels in the body. And for the part that we're interested in, right, the brain, they had about 140. So a lot less than what we have from the MRA, of course, but still. And then what they've done is they tried to be reasonably accurate. So they did 1D Navier-Stokes simulation on that. And that's what we used to fit the parameters, right? So we truncated our network at their level, and then that allowed us to optimize the C and the K, right, by using their terminating pressure. And there was another benefit to this. What we saw is that there was almost a very good relation between the terminating pressure they were obtaining and the path length on our graph. And so this suggested that this was a good way to determine the terminating pressure when using the full graph now, by simply imposing this relation. So this is what you have, right? This is what I'm talking about. So this is the pressure, right? And this is the path length. And you see that it's not perfect, but it's not that bad. And so that was very, very useful because, again, we needed to fix the terminating pressure, and now we could use this, this relation. And so this is the kind of comparison that, that we had now on the full graph, comparing it. So you see that we have a lot more points, right? For the simulation than varies for their model. We have more blood vessels. But when the points are comparable, it's actually not bad, right? Some of them are a little bit more off, right? But not so much. And you see that, especially if you compare the two pictures to the right, the qualitative agreement between them is quite good. So we were not unhappy about the result, okay, given the quality of the data that we had to start with. All right. And then we can do what we wanted to do from the start, right? Which is actually look at all of this. So this is now some actual simulated flow on the data set, right? The left is this one patient with very high resolution, and the right is, again, one patient for the still healthy, right, from the other data set. You see what it looks like, okay? So pressure goes down. It's relatively, yeah, so what I should say is that it's more visible here. The color of the color of the nodes, right, is the pressure. The color of the edges is the velocity. Okay, so this is what finally we can do. And we also performed some sensitivity analysis, which was a first step in trying to understand whether we could detect adaptivity with this, right? So, so what we've done is we've reduced the radius of a certain number of branches, right? Thinking, well, that might stimulate the effect of having a tumor, which is compressing everything locally, for example. And we did 3 settings, right? We picked up just 3 to 10 branches anywhere in the network. Then we picked into a subtree, or we actually picked a subregion. Right. And so you see you see the changes here, right? So this is the first case, and with 30% reduction in radius, right, when this is done almost everywhere, there's not a big effect, right? Of course, with 70%, now you start seeing something. This is the subtree, right? And with the subtree, actually, you see something a lot better because you see the localized effect, right? And this is the subregion. And again, you see, so there's a few changes, right? But you see that this is reasonably robust. With a 30% reduction, it's not like so much is going on. Of course, with a 70% reduction, now it's more striking. So this was reasonably, let us be reasonably optimistic about what we could see with that. All right, so now let's go to the actual patient for whom we had the full data. And let me describe a little bit what happened to her. So she was admitted to the NIH in 2008, right, with a brain tumor. It was a low-grade neoplasm, so, and she enrolled in a clinical trial. And for 4 years, essentially, this was what it was, and then it started to change, right? To a mixed low-grade, high-grade. High-grade is where you're going to glioblastoma, and this is the bad news. Right? So when she went high-grade, she had radiation therapy. Doctors know that they have to move aggressively in a case like this, right? And after further exams, surgery, right? And as is relatively typical from what I understand in Vu's case, that only postponed things a little bit. So essentially a year after the high-grade neoplasm was back, she had another surgery. And yet a year after, again, the tumor transformed, and she died. And this seems to be a relatively typical evolution of the disease, unfortunately. We have the first surgery. So we have a series of MRI brain perfusion, right? But those are 1 millimeter resolution, right? So they are really not that great. Except one that was done at the time of her surgery, right? In 2013. So we ended up having 5 time points that we could use from 2010 to 2013. And what we did here, right, is we used the arterial structure that we could get out of the good MRA. And it was not so great because the tumor already evolved, so the arterial network was already damaged in some part of the brain, and you're going to see that. And then we used the other data sets that we had to try to supplement this in between. All right, so this is essentially the end, right? So you see 2000, the red parts are the bad ones, right? The high-grade lesions. So you see 2012 and 2013, then there's surgery, but in 2014 it starts again, then there's another surgery, 2015 it starts again, and you see every time in a different region, right? And 2016 is the last one before death. All right. So this is what we ended having from the high resolution MRI. Right. So you see the circle of Willis, right? This is not a graph. This is not a tree, right? You see the circle of Willis at the root. And you see that after the circle of Willis, you have trees, right? As I said, it's not as detailed as we could have hoped because having the high resolution MRA when the brain was already very, very much impacted by the tumor, well, the resolution was not enough then. Plenty of the blood vessels were not super visible. But we can still do blood flow, right, on that, so that's what we've done. So this is the result of a blood flow calculation in 2010, right, when everything was okay. And you see that it doesn't look bad, okay? And in particular, it looks reasonable in each subtree, and the pressure is not the same, right, in every part of the brain. You see that here it's considerably higher than there. Again, this is not something that was surprising for doctors. This is essentially something they are expecting. Okay. This is the second step, right? And you see that here something happened. It's definitely not the same flow anymore. and here as well. So you see that it changed basically everywhere. Only this part has remained essentially untouched. So this is already, and you see that the pressure has increased pretty dramatically here. And this, as we understand it now, is a very big warning sign that something bad is already going on. Right. And you see the further evolution. So it's fairly clear in that case that the blood flow pretty clearly follows the evolution of the disease. Of course, we know the result, and as I said, it's only one patient, right? So it's hard to say if we do that in a blind testing, can we actually accurately detect the patients who are going to have an evolving glioblastoma from the others, right? This is what we would like to say, and this is what we cannot say because there's only one. Now, if we had 50, right, and we had seen the same thing on the 50 patient with glioblastoma and nothing at all on the ones without the glioblastoma, then we could have said fairly accurately, yes, this is going to be working. But having only one patient, it's impossible. So we did a first paper with this, and then we thought, how can we go further? Because without data, and then the next idea was to say, well, actually the NIH doesn't have more data on glioblastoma patients. What they do have is data on another type of patients that are sickle cell patients. And then we thought, okay, that was not the original goal, but maybe it is worth spending a little bit of time on that. And I'll take 5 minutes to show to you what we were able to do. Unfortunately, at that point, Henri took a job in Israel in a startup. So I'm not quite sure what's going to happen with the end of this study, but because I don't have access to the data. But at least on the sickle cell, it is working reasonably well. So let me explain that. This is a much better, so sickle cell is a blood disease, right? So on the other hand, everyone believes that the blood disease will have effect on the evolution of the blood vessels. Right? And here we have a good data set. So we have plenty of patients, and we have at least 3 data points for each one of them. All right, so here's the evolution, right? This is one patient. Everything is anonymized, of course, right? And again, this is the evolution of the mean radius, right? Of the various blood vessels in this compartment, right? Along the 3 data points. You see that, well, things happen, right? Obviously. So we were very happy with this till we did the same with a healthy patient. And then it seems even more stuff is happening. Now again, it's not necessarily a big surprise for doctors, right? Arterial networks are not frozen in time. Especially at the level of the small blood vessels. This is something that they do obviously change in time, right? The topology remains the same, okay? But the evolution of a radius. So right? This is now the histogram, right, of some of the patients. So the first row are healthy people. The bottom row are people who are sick, so with sickle cell diseases. Up to there, you see that it's really all over the place, right? But if you work a little bit more, and what I actually did at that point is I had one student run a clustering algorithm to try to make sense of the whole thing. And it turns out that if you're looking at the right LP norm of the arterial network, then you have a pretty clear separation between healthy and non-healthy patients. And this is the so this is the case, right? So here I took 5 patients of each, right? So I'm using an L 0.5 norm, and you see that here you have a fairly obvious threshold at around 4,500, right? Except for one healthy patient that took us a little bit of time to understand what was going on with him. And the problem is that patient had 2 MRI at very short time interval. And because we are calculating rate of change, we are dividing by the time difference. And so this gave number that were completely artificially high. And probably just because we are seeing noise here, right? So this was not a real change. It was just if I'm doing 2 exams very close to one another, there's always a little bit of noise, so you're always going to be a little bit of change, right? And that change, if you divide by the time difference between the exam, of course, you can blow up the numbers completely artificially. So now then we learned how to remove this kind of cases from the data set. So that was fairly optimistic, right? Again, I'm not so sure where this is going now, unfortunately. And it's essentially time to conclude as well. So I think the conclusion here is yes, current brain imaging, first of all, it can be used to get a relatively accurate representation of the arterial network. And then, at least at the qualitative level, maybe not at a fully quantitative level, but at a qualitative level, this representation is good enough to understand changes in blood flow in those networks. So for sure, there's a lot of potential here. To go further, as very often in this kind of applications, we need more data. And there needs to be a bit of a push, right, so that patients actually receive more accurate MRI and MRA in cases like that. And some doctors are aware of that. Of course, it's very, very hard to change a medical protocol. And those things are expensive, as I said, which is another reason why it's not that easy to do. If we could have more data, then maybe we could actually learn a lot more about the disease thanks to this kind of techniques. As it is today, I have to remain careful. Again, I can only say this is promising. Thank you very much.
Has some questions or comments in the room before we go on to the next chairman? Yeah. They asked us to use the microphone or the sound will go on
for the people online.
Hello. Very nice talk. But I was wondering if the wood flow, is it pulsative? There are pulses, or is it continuous? And whether these oscillations may affect on the velocity and pressure calculation, and whether they may also, in turn, determine how it's going to affect also the...
Yeah, by calculating steady flow, for sure, we're making a mistake. And if we, I have it. In particular, if we were trying to actually solve Navier-Stokes with a fluid structure interaction, I think you would see a very big difference between trying to calculate a steady flow and actually trying to calculate the flow with a pulse. Because of the simplistic model that we are using, I'm not sure this matters so much. The model is already very wrong. So we probably just have some, you know, I wouldn't say it's more than qualitative, right? I wouldn't expect that we can estimate the blood flow, the pressure at plus or minus 10%. Even though we have a good fitting with an actual Navier-Stokes calculation, right? It's, as you know, it's always easy to fit things, right? That doesn't mean that they have a very good predictive value. So I would only take that as a qualitative understanding. So if the pressure goes up, it probably goes up, right? Whether it goes up by as much as what is shown from the simulation is, I don't know.
Hi. So I have a practical question. In that example of that poor person who died in 8 years, the topology of the blood flows of the vessels was the same all the time. Now, in my head, naive, I've never thought about this. I would think the cancer disrupts it and breaks it. So can you clear that up for me?
Yeah. So probably. But we couldn't see that because the first MRI we had, the cancer was already there. At the level and the consequences, this is not as precise as we would have expected it to be. And if I'm going back. So this and that have the same resolution. And yet this is so much less precise than this one. It would have been so helpful to have an MRI before the glioma was there. What you're describing probably happened. It's just happened before we could see it.
Angiogenesis described in GBMs. That's something that people expect.
Yes, that's what. But more than angiogenesis, it's probably moving the blood vessels, crushing some of it. So locally, you probably, at the scale of the small ones, you probably have quite a bit of changes. Whether this leads to angiogenesis somewhere else could be. I'm not really competent to answer that, but for sure, I think there are changes in the topology, right? In the sense, I don't believe you keep the same arterial network. You probably at least lose some blood vessels in some regions.
But losing, maybe you can follow by making your diameter go to 0 in your model, while creating new things you wouldn't, right?
The problem is measuring it, right? It's not that our model is trying to predict the evolution. It's just observing the evolution and trying to draw conclusion out of that evolution. But if we cannot see, we cannot see, right?
Okay. Any more questions?
So thank you very much for the talk. I got a question about the poor sick patient. Could you maybe go to the time evolution of her blood vessels again, please? So it was this middle right part that where the pressure went up, and do you know whether this is actually the part where the tumor was?
Yes, I think the tumor was actually here.
Okay. Okay. That's also quite interesting. Maybe also to compare it with other patients if there's more data, of course.
You know, as I said from the beginning, that's the flow in all of us, right? What you would need here, you would need to have 400 patients. You would need to do that for 400 patients, and then we could start talking about what kind of solid conclusion we can actually draw.
Sure, thank you.
Thanks. I think I'll just move to the internet questions if there's some, because we're a bit behind.
So there is a simple question. Would this help to monitor or to find a way to deliver drugs to the brain tumor?
That's a good question. I don't know, actually. Well, knowing a little bit what the arterial network is like could help, I guess. But modeling the blood flow, probably not. Because anyway, right? I mean, the question is whether there is a flow or not if you want to deliver the drug, I imagine.
Okay, so I think we'll stop here. Thanks again, Pierre-Emmanuel. Since we are nearly at the time we should start the next talk, let's just postpone it 5 minutes and start at 10, okay?
every time until your hands dissolve. Well, if you do it every time, then
I'll just start with one sad announcement, is that our first speaker of the afternoon will also be on Visio, because he's a contact case for COVID. And we will have two speakers this afternoon on Visio, the first and the last, if I'm not wrong. Okay, so now for our next speaker for this morning, we are pleased to have Markus Schmitzen from Dresden, and who's going to talk on incompressible limit for a tumor growth model incorporating connective effects. Thank you, Markus.
Thank you, Luce, and thank you to all of the organizers for putting together this workshop and having the courage to actually hold it in presence. I was also not convinced that it's going to take place in presence, so thanks a lot. And for me, it's also been 2 years that I've been to Paris the last time. And so, it's a great place for mathematics and academic exchange. So I'm also very pleased to be here and present some work I've been doing in collaboration with Noemi David. And so it's on an incompressible limit for a tumor growth model. And so the question that I want to address is a very fundamental one. So, so on the top row, you see two experiments, biological experiments. And so essentially here we have human embryonic kidney cells. There we have some tumor lines. So from my collaborators, Hideki Murakawa and Daniel Cohen. And so what we see is that as time goes by, we have these two cell populations migrating towards each other. So there's also a video. And so the question I want to address today is that as applied mathematicians, we always have a question to face, a choice to make, namely how we want to model, and in this case, how we want to model living tissue. And so on the left-hand side, I've just plotted some graphs, so lattice-based models where we essentially have individuals, so each cell is being described by its location on some discrete lattice, and then we prescribe some evolution on this lattice. Or alternatively, we identify each cell by its coordinate, and then we describe how the cells interact and then move according to surrounding cells. And so another choice is a macroscopic description, as we can see here, which instead of describing the evolution of each individual cell, describes the distribution of the cells instead. So how likely are we to find the cells at a certain location? And this is described by a continuous variable, like here. And then there's yet another approach, and that is the approach that I'll be talking about today, is this geometric approach where instead of tracking each individual, or instead of tracking the density of my cells, I describe my tumor, say, as a set that it occupies, and then how the set evolves as time goes by. And so historically, there's been a lot of work scaling limits of how you go from an individual-based kind of microscopic approach to a large scale, to the macroscopic scale. So for instance, by mean field limits or other scaling limits. And recently, there's been a lot of interest in how we can actually bridge this gap between a density-based description and this free boundary flow. And this is what I would like to address today. And so the very foundation for the model is, so we start with this macroscopic approach where the tissue is described by its density, which will be denoted by n of x and t throughout the entire talk. And I'd like to incorporate three mechanisms, essentially. So there's a pressure that avoids overcrowding. There's some drift, and this is the novelty of this work, and some cell growth and death. And so the equation that this gives rise to in the simplest setting is this continuity. Oh, I shouldn't be pointing. The continuity equation, essentially where we have this pressure term, so it's coupled through Darcy's law. We have some drifts, and we have these growth dynamics. And of course, there's different ways how we can couple the velocity to the pressure, and here we'll be interested in Darcy's law. So it's just essentially how you can imagine this is that cells will tend to flow downhill the pressure gradient in order to avoid overcrowding. And so in this talk, we'll be assuming this compressible pressure law. So essentially what you can see here is that as the density increases, the pressure grows, right? So the more cells you have, the higher the pressure on that tissue. And so we just choose this power law here. And so the incompressible limit consists of linking this macroscopic description, so this partial differential equation, with the evolution of this patch that the tumor inhabits, if you will. And so to fix ideas, I'd like to invite you to join me in a very nice computation, which I find quite fascinating. So we start with the power law, and then we just do a small modification. So you see if we cancel the k minus 1 here, then we have a factor of n to the k minus 2. So, I mean, these two lines are exactly the same. And then we continue. So we just multiply by a 1 in here. And so what you can see here, this term is exactly our pressure, right? By the way we chose our compressible or constitutive law. So let us replace this term by the pressure, as we've done here. And so in the final step, we just split this exponent on this guy, on this term, and on that term, respectively. Okay? So we've kept the k, so this fraction here, the n has moved there. And then we have, these fractions sitting here. And then p, the pressure, so this guy, raised to the k minus 2 over k minus 1. And so now the incredible thing that happens is as k gets very large, so as k goes to infinity, we see that this term is essentially 1. This term is also 1 raised to the power 1. And then we have p raised to the power 1. And so what that means is that if we have limit quantities n and p, they will satisfy this kind of complementarity relation that p infinity is equal to n infinity times p infinity, or, well, if we rearrange the equation, we have this equation. And so this tells us something about our tissue, namely if the density is not saturated, so if the density is less than 1, then we do not feel any pressure, or the pressure is equal to 0, or if we like to think about it the other way, if we have a positive pressure, then it means that our tissues or our cells are saturated. And so if we somehow have now like a link between this macroscopic description and the macroscopic description and this free boundary, this patch of cells, namely the set where the pressure is positive, more or less. And so what's going on here is, so I've just taken this power law and I've plotted it for several values of k. And now you can see why this limit is called stiff limit or incompressible limit, because essentially the cells do not react to the pressure as k gets large unless our tissue is saturated. And so this is the limit that I'm interested in, because then we can make this identification. Okay. And so before we go into the mathematical details, I'd like to give a bit of a historical flashback, because essentially the topic started about 60 years ago with the well-posedness theory of the filtration equation, so by the famous Olejnik and collaborators. And then from there, Benilan and Crandall showed the continuous dependence of this nonlinearity, so this phi. So solutions will depend in a continuous manner on the nonlinearity phi. And so if you choose a power law, so if the phi behaves like a power law, then, in the 1980s, there's this British group that observed, by using formal asymptotic expansions, that as k gets very, very large, your density distribution actually looks like something that is flat. Flat like these mesas, so these mountain structures where you have a flat top, and then there's some small things going on, and then there's, again, a patch of where the density essentially is saturated. So these mountain structures are called mesas, and so this limit historically is called the mesa limit. And then, 1 year later, by Caffarelli and Friedman, they gave a rigorous foundation for this limit, a justification. And so now the question is, so we've already got a bit of an intuition about what's going on here. So why do we get essentially indicator functions, so sets or where the density is saturated, and then some, well, other zones? And so the answer is, well, we have to study the equation. We have to have a closer look at just the pressure term in our equation, right? So I've just substituted the pressure in here. And so if we apply the chain rule, then we see that we can write this as a diffusion equation that has this nonlinear mobility. So k times n to the k minus 1. And so what does that mean? So whenever n is between 0 and 1, so whenever we're not saturated, the mobility is 0. And whenever n is larger than or equal to 1, the mobility is close to infinity. And so what happens is in this limit, so we start with this gray curve. As k gets large, in an infinitely short period of time, we have that these mountain hills, quote unquote, will collapse. So mass will be diffused or transported, depending on how you like to look at it, to, well, the next possible space. And so what happens is that we have exactly these indicator type functions and then some density between 0 and 1. And so now that the thing is we want to identify these saturated zones with where the pressure is positive. And this is then how we build, this is our formalism of how we build the bridge between macroscopic and geometric model. And so one absolutely crucial instrument in this, in the mathematical justification is that we observe that this, the dispersal of the density driven by the population pressure, so this is this term, actually corresponds to a porous medium equation. So it can be written like this. And so there has been a very influential paper by Aronson and Benilan that gives you a very strong regularity result on the Laplacian, so second derivatives of the pressure, in the following way. And so you see that this bound depends on k. And so as k goes to infinity, this will go to 0. And actually, this result is very, very important, not just in the topic of incompressible limits, but also a lot of like fine estimates on the porous medium flow. And so this is one crucial tool that we'll be devising, and in our work that we've kind of extended or, well, find a novel approach to make it fit for our setting. So then the story kind of continues. So so after these fundamental works or seminal works, there was a paper by Gilles and Quiros where essentially they take a half space and then they have an injection at the origin. And so then they see how the free boundary propagates. And then, well, a couple of years later, there's the cornerstone or the stepping stone for our work, which is a paper by Pertam, Quiros, and Vasquez, where they prove this Healy-Short type asymptotics for, in the context of tissue growth or tumor growth. So instead of having an injection that drives the free boundary, like in a Healy-Short cell, it's the growth dynamics of the tumor and the incompressibility that drives the growth of the tissue in this setting. And then from there have been various generalizations for various pressure laws. So there's this work by Hecht and Vauchelet for the singular pressure law that already incorporates some level of incompressibility. Then nutrients have been included in the dynamics by David and Pertam. And then also the strategy was extended to systems of interacting species. So for instance, normal and abnormal cells. In the case of the singular pressure law, we've also worked on this for the power law case. And then this was extended last year also to the full space. So up to this point, we only had one-dimensional results. And then quite recently, there has been another approach for non-monotonous growth rates, let's say, by Gillen, Kim, and Millet. And so what I did with Noemi was we wanted, so up to this point, there have been various generalizations, but we didn't have any satisfying answer to what happens when we include drifts to the dynamics. And so drifts are very important in tissue growth, you might argue, because, I mean, if we have, for instance, an oxygen distribution or nutrient distribution, this might induce a favorable, like a direction towards, or a motion towards a favorable zone. And so this motivated the question of how we can treat this, geometric limit in the case of convective effects. But still, I'd also like to say that this is a very, very active area. So there have been many people studying certain aspects of this model, and essentially there's three communities. There's the people from optimal transportation that have a kind of a gamma limit approach to this, this type of problem. There's people working in viscosity solutions that give you a very fine description of the free boundary. And then, let's say, the classical quote-unquote Sobolev theory that lets us describe, or that lets us derive the equation that is satisfied inside of our tumor patch. Okay, so as I was mentioning, the stepping stone was this model by Pertan, Quiros, and Vasquez, where essentially we have these two effects, a pressure and a growth term. And so what they observed is that if we multiply the equation by p prime, we see that here we get an equation for p, and the equation looks like this. And so if we substitute our value for p, we see that we have a very large term appearing. So k is the quantity that goes to infinity that helps us establish the link between macro and geometric scales. And so as k goes to infinity, so this incompressible limit, we have exactly this, this Healy-Shaw type problem. So whenever our pressure is positive, so inside of our set, inside of the tumor, we have to satisfy this elliptic equation. And this then will drive the boundary of our tissue. And then, so in their paper, they can also identify exactly the zone of saturation with the zone where the pressure is positive. And so what we did, as I foreshadowed, is we wanted to incorporate convective effects. And so now our model accounts for this pressure-driven dispersal. So if the tissue is too packed, it wants to expand. We have advective effects due to favorableness, so oxygen, nutrient gradients, etc. And we have the mitosis and apoptosis effects that also depend on the pressure. And so formally, again, we can multiply the equation by p prime. So actually, I've done a bit greater detail here. So we have p prime times dn by dt, which is a chain rule, so it's dp by dt. Here we have p prime times gradient n, which is a gradient p. We have another gradient p here, and then we have this p prime times n term, which if you write it down, it gives us this k minus 1 pk, right? Because this is a power of n. And so formally, if k goes to infinity, then only the last term matters. It becomes dominant. All the other terms vanish. And so we would expect to get this complementarity relation. So this is the equation that governs the pressure inside of our tissue. The question is, you want to pass to the limit here in a rigorous setting, so how do you get the compactness of, and what's needed here, the pressure gradient? Right? So you need very strong compactness results. And so this was the challenge, and this is what I want to tell you about today. So this is just one slide to show you, again, the connection to the Healy-Shaw dynamics. So here we have in the zone where the pressure is positive, we satisfy this elliptic equation here. And then at the boundary, the pressure drops to 0. It's 0. And this then drives the evolution of the free boundary. So this omega is really an omega of t that grows. OK, so then, as I was saying, how can we justify this limit, k going to infinity, given that we have to have the strong compactness of the pressure gradient in order to pass to the limit in this term? And so there were some previous results in the literature on equations with drift, but they were not able to get this type of strong compactness. And the reason is that, in a sense, the Aronson-Binilan estimate, this classical parabolic result, fails, and it fails in a way that essentially the Laplacian of the pressure can only be bounded by a constant minus something that vanishes at 0. So it's essentially the problem that arises in this context. And so we wanted to circumnavigate this problem, and well, we came up with a different approach that well, uses essentially less assumptions than the few results that there are on the equation of drift, and we can still pass to the incompressible limit. So we can still rigorously justify how we go from macro to geometric description. And so the assumptions that we impose on our model are essentially, we have non-negative densities. Sure, they're compactly supported and integrable and bounded. And here we also assume that they're BV. And of course, so this is not unusual to assume, because what you have to keep in mind is that if we want to have a mesa limit of this type, then we have to allow for these jumps here. So this is a minimal requirement. So this is not too crazy. Then for the growth rate, or the death rate, we assume that it's a C1 function that is strictly decreasing. Okay, so I've just given a cartoon here. And we assume that there is such a number, Pm, called the homeostatic pressure, where our growth rate drops to 0. And the motivation for that is that when the tissue is in homeostasis, so when it's in equilibrium, if you will, then as if the pressure is slightly larger than that, our tissue will start dying. Whereas if the pressure is lower than the homeostatic pressure, then essentially there's still room for our tissue to grow, and therefore the growth rate is still positive. So this is the motivation for these assumptions. And then concerning the drifts, and this is the novelty, we need some third derivatives in something slightly better than L2. And so this is the mixed derivatives, so we also need some minor integrability. So it's a bit tedious, but essentially some assumptions on the drift are so that we can still propagate this BV, these BV bounds, and then there's some assumptions that we really need in order to get the strong compactness of the pressure gradient itself. Okay, and so based on that, now I can present the results that we obtain. So on the one hand, we have the strong compactness of the pressure and the density itself. But that's, I guess, maybe not so surprising. What's more surprising is that we also control the derivative. So we control the gradient, and we have strong compactness in L2 of the gradient of the pressure. And so with that, then all the terms in our equation, so that we can pass to the limit in all of these terms. We can justify it rigorously. And what is more, we have these two complementarity relations. So the first one that I showed you, and then this one that essentially tells us the pressure distribution inside of our tissue. And moreover, we can show that N and P at the limit are uniquely determined quantities. Okay, so basically I wanted to split this, just like we split our paper, into two sections, let's say. So there's one on a priori estimates that are more or less for free, I'd say. And then there's the ones where we have to work hard and where we actually found some new regularity theory. And so the ones that are for free are these L1 estimates, because we can just integrate the equation for the density. We have some L infinity control, but this is due to the fact that essentially if we take a Barenblatt profile, so a self-similar profile, we can always put it on top of our density, and then we can control by comparing with this larger profile, we can control the L infinity norm as well. And then we get control of the pressure gradient, which tells you it converges weakly, but not strongly. Let's keep that in mind. And this is, follows from studying the equation for the pressure itself. And then the final set of estimates is these BV norms. As I foreshadowed, that's why we also imposed this initially. But all of this is not enough to justify this elliptic equation inside of our tissue patch. And so that's why we need a second set of a priori estimates that give us the strong compactness of the pressure gradient. And so there's two ingredients that allow us to obtain that. And so the first one is an L4 estimate that Noemi and Benoit have shown or proven in a previous paper in the case of nutrients. And then we combine that with an LP version, so not an L infinity, this lower control of the Laplacian, right? But an integral version of the Aronson-Benellan estimate. that's been explored by well, my collaborators and I in some recent papers. And so essentially what we get, instead of having a control from below on the Laplacian of the pressure, now we control the, well, the negative part, but in some LP, so in L3 in our case, so in Lebesgue space. So essentially the key message is we do not need this lower bound. We can also get away with some integrability of the negative part of the Laplacian. And so now we have all of these different estimates, and we want to piece them together to complete our puzzle. So from here, this will allow us to get the Laplacian in L1 uniformly. We already have the strong compactness of P, and we know that the pressure gradient is in L4. And if we combine all of these things in a good way, then this will yield the compactness of the gradient of the pressure in L2. This is what we were after. And this ultimately allows us to justify the complementarity relation, right? Only if we have this, we can pass to the limit in here. So how do we do that? Well, I've just removed all the unnecessary terms, let's say, just to give you an idea of what's going on. So I've removed the convective term, I've removed the growth term, so we've just taken the equation for the pressure, right, without growth, without drifts. And what we can do is we multiply this equation by minus Laplacian P, okay, as we see here. And then, so if we integrate by parts in here, we have gradient P, dt gradient P. And so this is essentially the evolution of d by dt of the L2 norm of the gradient. So this comes from here. And then here, we keep this term because it's already something negative, so we put it on the other side. So this will also be controlled by the estimate. And then there's only this term left. Okay? And so if we massage it a little bit, then the final estimate that we obtain, it's not exactly the same because we still have to keep track of the drift terms, the growth terms. This is just purely for the diffusive or parabolic part of the equation. But you see, if you study the evolution of this first order functional, so essentially 2 derivatives on P, you get a control on essentially 4 derivatives on P, as here and in here. And so this is the first observation that we use. The first ingredient is study the evolution, or study the dissipation of the gradient of P in L2. And this gives you some control of the Laplacian and the second derivative on the support of P. And then the other one is a neat trick that Benoit and Noemi discovered. So if you take the L4 of the pressure gradient, you can write it as a gradient squared times a gradient squared, of course. And then we integrate by parts, so we move the gradient onto this guy. And if we expand all the terms, okay, so we take this, we integrate by parts, we expand all the terms, then this is what's left. And now we just do a Young's inequality. And we see that, okay, we start with the gradient in L4. We get another gradient in L4 from here, right? And this is the other term from Young's. And we get another gradient in L4 from here, and this guy. And so we subtract these two things, and what we obtain ultimately is, well, a quarter, but essentially a gradient in L4 is bounded by, well, these second order functionals. So the Laplacian squared and the mixed, or all derivatives of P squared. So this is the second thing. And now we want to join them. We want to merge them. Because if you have a closer look, this term is controlled by this one, and this term is controlled by that one, because we have that the pressure is in L infinity. So it's a bit of a tricky computation, but essentially what we've obtained is we get an L4 control by studying the dissipation of the L2 norm of the gradient, which is one of the crucial ingredients, if you remember, in order to then justify that the gradient converges strongly. The other thing that we need is this Aronson-Benilan type estimate. And so historically, the classical estimate uses a comparison argument, which in our case, well, we don't want that because we have these drifts. I mean, we know what the comparison looks like. So instead, we take the equation, we differentiate it twice, so we pass to the Laplacian in the equation. And then we call W minus the Laplacian of the pressure. And then we obtain an equation for the negative part of the Laplacian. So essentially what we do is we study the evolution of a second order functional now. And what happens is that if we do all the analysis, which is lengthy, and especially with the drifts and with growth dynamics, what we observe is that this functional, so this integral, is being dissipated in the following way. Right? So we get an L3 control on the second derivatives, well, the negative part of it. And so then we can integrate it, and we see that the Laplacian of P, the negative part, is integrable in LP. And so these two things are exactly what we needed. So we have a second order control of the pressure, we have the gradient of the pressure in L4, and we have that the pressure converges strongly, and we amalgamate all of this information, and then we have the strong compactness of the pressure gradient, which allows us to pass to the limit in here. This comes from the strong compactness of the pressure, and so this is rigorously justifies this complementarity relation that governs the flow of our boundary. And so what is more, we can show also that the limiting density stays between 0 and 1, and we can pass to the limit in the equation for the density, and we have the second complementarity relation. And the final thing that we need to show is that the limit is unique, right? This is the only thing that we claimed and haven't shown yet. And so to this end, so we use a strategy that was already introduced in the paper by Pampiros and Vasquez, and we adapted it to incorporate drifts. So what we do is we study the difference, I mean, it's the standard thing to do, between two solutions, so N1 and N2, and P1 and P2. We test it against some test function psi, and then we just take the integrand and we rewrite it. So we factor out a z. At this stage, it doesn't matter what it is, but I just want you to focus on like copying all of these terms. We divide by z and we multiply by z. And then the last term, so we do this for the time part, the second order derivative on the pressure, which now sits on the test function. This is the drift part. And then for the growth, essentially we've written this in a very complicated way, but this guy, the gray panel and this gray panel add up to 0. The difference of the p's cancels, and so we get back exactly to this line divided by z and multiplied by z. So why on earth would you do this? Well, now we can substitute these, so we give those special names, these quantities, and then we can rewrite our equation in the following way. We factor out a z, and then we have essentially a backward equation for psi, right, with these coefficients a, b, and c. This is what we get. And now the final step in this duality trick that we use here is, well, the equation for the difference is essentially equivalent to this one. And so we haven't chosen psi, our test function, yet. We just said, let's take an arbitrary test function. Now at this stage, we take a special one, namely a psi, such that the whole equation is equal to a times yet another test function. So there's two test functions, but now we set psi to be the solution of that. So the solution of this red part, which is equal to a times psi. And all of a sudden, this complicated looking equation boils down to, well, we replace all of this by a times psi. And so since a is n1 minus n2 divided by z, we have this cancellation here. And so what we're left with is n1 minus n2 times psi. And so now this looks really neat, because this essentially gives us the uniqueness of n1, because we haven't set psi. We just said we chose any psi such that our psi satisfies this equation. Now we choose any psi that we want, and we have the uniqueness of n1 and n2. And so then the final step consists of having a look at the weak form again, using the fact that n1 and n2 are the same. So these two terms, they drop from our equation, and the only term that remains is this one, and the growth terms, like here. And so then you can see if we substitute the difference of P1 and then P2 for the psi, and we integrate by parts, we get the gradient of the difference squared. And this is equal to n1 times the difference of the g's times the difference of the p's. And now, since our tissue, our growth rate depends on the pressure in a monotonous way, right? So the growth rate should drop as the pressure increases. We see that this term always has a sign. It's non-positive. And so we've shown that essentially a non-negative quantity is less or equal than 0. And this can only be if the gradients match. And then from there, we infer that P1 has to be equal to P2. And so there we are. This shows that initially that the equation for n has a unique solution, and therefore the equation for P has a unique solution. And so this is all that we did in this paper and that I wanted to present to you today. And I'd like to close on some future work that I want to conduct. And so the first one is it's a very tricky question. So during my time in Paris, actually, I've been quite involved in this Brinkmann type equation that incorporates viscoelastic effects. So now our model only has some say, friction or interactions with the extracellular matrix. Now we want to have friction between cells. And this was a model that was proposed by Bouchelet and Pertam. And so we have this viscosity sitting here. And now you could say, well, if nu goes to 0, right, then essentially this potential W will be equal to P. And so you would expect that from the Brinkmann law, you can go back to the Darcy law, right, but just by replacing W by P. But so this estimate requires, well, this building this bridge between these two models requires a different set of stable estimates that is, well, up to this point seems very tough. So this is something that still has to be studied in greater detail. And then also associated to this problem is the two-species version with different drifts. And so I think this is a model that I'm proposing since many years. And one thing hasn't changed. And the thing that hasn't changed is that not even existence is clear. Right? So many people have looked at this from different viewpoints. So again, optimal transportation, viscosity, certain types of approximations. But the problem is that this is really a wolf in sheep's clothing, because you have this this term essentially behaves like a hyperbolic equation, but it is parabolic. And so you don't know what tools you have to combine in order to justify, to give a meaning to the equation and to show existence. And the same is actually true also for different mobilities. If we were to include, say, if we were to assume that the cancellous tissue moves or diffuses or responds to pressure faster than the normal tissue, then I know of one existence result. And it's one dimension and for a very special solution. And the final thing is, so if we go back to the two species that I've shown here, so we have these different approaches, microscopic, macroscopic, and geometric. And so this is, again, this blob of tissue. So we really see that it behaves as a bulk. But when you have these, when the two species interact, we have these internal layers that gives you an additional, problem in terms of regularity, because now you have internal layers on top of the free boundary. And so what I would like to do is build a direct connection between interacting particles, so the microscale, that allows you to go directly to the geometric description without passing through the macro scale, essentially. And so these are the open questions. So there's some work in this direction, but it's very, very preliminary. And OK, I guess that's all I wanted to talk about today. Of course, I would like to thank my collaborators, because, I mean, this is one work out of many with my Parisian friends here. And so, yeah, thanks a lot for the invitation. And yeah, I'd be happy to answer questions.
Okay, thank you, Marcus, for your very nice talk. Are there some questions in the audience? None that I see of. Just one thing, when we're looking at this last interacting species issue, the boundary between the two species, wouldn't you expect it to have some fingering showing up? Or how would you get it in your model? Because it's looking very regular in...
Well, so this is actually like, so we had a chat with Daniel Cohn about this, and it depends on so in the biological experiments, actually, so depending on the initial configuration of your cells, you have some irregularity in the boundaries. So it's actually quite interesting because this is something that we don't observe in the model. So if your initial condition is like this, essentially initial condition for the biological experiments, then you have these cell protrusions, like these fingers that you see there, right? But then for these circular initial data, you see that the boundary is actually quite smooth.
You have fingering while you don't have the second species in front of you, but when you start interacting with it, then you sort of regularize your boundary.
Exactly, yeah. And so I don't know, we don't know why it happens that you have this. I mean, so this looks very regular in terms of like two interacting species. But you're absolutely right. If you have initial data like this, then the zigzagging behavior that you have here is more pronounced. And unfortunately, I can't explain where it comes from. But in the mathematical model, so if you just take the symmetric, so this is essentially our pressure, right? And so we've taken these initial data, and then you see that at least in terms of the model, the interface is completely straight. And so I don't know how to account for this, but maybe it's because when you pass from a stochastic macro model, then you do some sort of averaging that, sometimes it's like this, but maybe sometimes it's like this. So that's why you expect on the macro scale, you don't get this type of resolution.
Okay. Okay, any other question in the audience? No? Do you have some internet questions?
Question is, are there concepts of energy in these problems which could help?
Well, so for the parabolic part, you have some energies, and also for if you incorporate drifts, right? And so, if you have energies of this type, so some k norm. So this would be an energy that is associated to and so, yeah, you're right that essentially this gives rise to a sequence of energies with a sequence of minimizers, and so then this gives rise to a sequence of problems, and this is exactly what the optimal transport community does, right? So what you do here is you have a sequence of energy functionals and minimizers, and so the natural thing to study is gamma limits, right? And so the limiting energy functional would look like essentially still phi n, and then plus an indicator, like what's it called? So essentially plus infinity if n infinity is larger than 1, and 0 otherwise. So, and this also gives you an incompressibility, or like an incompressible fluid. So, for instance, Sant'Ambrogio has been very active, and Henri in the context of traffic flow. And essentially, this pressure term then becomes the stiff pressure in the form of an indicator. So you have a convergence of energy functionals and convergence of associated flows. But actually, an interesting question also is how you incorporate growth dynamics, because then you have to construct different metrics.
Okay. You have to understand that there are 20 seconds difference between YouTube and your talk, so I will tell. So it seems okay.
Okay.
Okay. Thank you very much, Marcus. So let's thank Marcus again if there are no other comments. And so normally we are supposed to reconvene at 2 o'clock. Since it's online, if some of you guys want to stay elsewhere for the first talk, but you can also come here, and we should be projecting the talk on the screen. So it's up to you to come or not. But then the other talks will be physical, so if you're somewhere else, you can't be very far if you want to follow the second talk. Okay, thank you. Enjoy your lunch.
reste. Test. Richard, can you hear us?
I can hear you.
That's great.
Hi, everyone.
Could you also please share your slides with us? Thanks a lot.
Tack.
Marvelous. Okay, welcome back to this afternoon session. Our first speaker is Richard Bayeul from Heidelberg and Geneva, who will be speaking to us about deciphering biomechanical drivers or morphological diversity in early animal development. Please, Richard.
Good afternoon, everyone, and thank you to the organizers for giving me the opportunity to talk today. Of course, I would have preferred to be there in person, but a virus decided otherwise in the last moment. Anyway, nonetheless, I'm happy to share with you some results of my postdoc project that I started a year and a half ago at Embol in the lab of ASAMICME and in close collaboration with the lab of Alba Munoz and the lab of Guillaume Salbot. So, in my postdoc, I am interested in the emergence of shape, morphogenesis, across evolution. So during development, from initially simple, embryos undergo a succession of finely orchestrated transformations that lead to the emergence of diverse shapes. The emergence of shape diversity is a long-standing question and complex question. And even though today biologists have acquired a lot of genetic data about what defines the polarity of organisms, and even though they looked at specific organs, understanding the diversification of body plans at the organismal scale still remains a big challenge. We lack unifying frameworks to tackle this question of shape at the scale of a whole organism. And one reason for that is the complexity of the body plans. In particular, the body plans, the shapes you see here of these vertebrae is quite complex. So to understand what defines the shape of organisms, we need a simplified version of the body plan. So for that, I propose to go back 600 million years ago, as I am focusing on a very old phylum called Cnidaria. Sorry, give me 1 second. Okay. Yeah, I'm focusing on an old phylum called Cnidaria. This is a sister group of bilaterians. So what are Cnidarians? They comprise a large variety of animals, like sea animals, corals, and another group, a large group called medusozoans, which comprises in particular hydroids, like the famous Hydra, Hydractinia, Clitia, and in particular also some jellyfish, as you can see on the right, on the bottom right of your screen. So as you can see there is a rich diversity of shapes within Cnidarians. And however, these shapes have a lot in common. They are acquired from just two basic body units throughout their life cycle, the polyp and the medusa forms. So yeah, they are actually very similar. One has the mouth and the tentacles facing up, the polyp, whereas the medusa has the mouth and the tentacle facing down. So in particular, a unifying feature of these Cnidarians is the polyp form. I mean here that all the species you can see here, even the jellyfish, at some point in their life cycle, they will transition from egg to polyp. Just as an example, Clitia, you see here in the bottom, this little jellyfish here, is actually bud from a colony of polyp here. This is the arrow on the top. Yeah, this is asexual reproduction budding. So how do we transition from an egg to a polyp? I will emphasize this in the species I work with every day. So Nematostella is the species we have in the lab of ASAMICME. So when the eggs are fertilized, they undergo cell divisions and diverse early developmental processes during which they keep mostly a spherical form. At one point, they will reach the blastula stage. So what we call a blastula is an epithelium surrounding a cavity. After that, the embryo will gastrulate. So in the case of Nematostella, gastrulation occurs like this. It's just an invagination of the tissue in the cavity from one pole, the future mouth. And so at the end of gastrulation, the embryo acquires, let's say, its definite body plan. So it has one axis of symmetry, the oval, so-called oval-laboral axis. It's symmetric around this axis. And it has just two epithelial layers, which we call ectoderm and endoderm. So this is a relatively simple organization of the body compared to us bilaterians or any vertebrates. Then there is an intermediate stage, the so-called planula larva, which is a swimming form of the animal, as you can see here. And as you can see, these planula are elongated along this same axis of symmetry, the oval-laboral axis. So to complete the story, after this larvae, this planula will settle and undergo metamorphosis into a pod. So today I won't talk at all about this metamorphosis. I will talk what I'm interested in, and what I will discuss today is this transition from a spherical gastrula to an elongated planula. And as you can see, the shapes of these planulas vary a lot across the phylogeny of cnidarians. These planula can be more or less symmetric. They can be narrow in the arboreal side, like or wide, like in Aptasia. They can even more narrow in the arboreal side, like in Hydractinia. The fact that the shapes of these planulas vary so much and that they are a swimming form of the animal makes this cnidarian a great model system to question not only tissue deformations, but also the functions of these tissue deformations on the organismal scale and the behavior of the animal, as they are a swimming form of the animal. So for my project, I am using this natural variation, this diversity of larval shapes, and I carry out comparative approaches. Namely, I am looking for common points and differences in the elongation process between the species, and I am to use mathematical modeling to find the parameters responsible for these differences of elongations. So, of course, I would love to understand all this transition you can see here, but so far, I have been able to work on these two species, the sea animals, Nematostella. So as I said, we have it in the lab. This is the species I work with every day. And Aptasia is kindly provided from a collaboration with the lab of Annika Goods, which is in Heidelberg, of organismal studies downtown Heidelberg. So I have described the dynamics of shape changes from gastrula to planula in these two species. Here they are. So what can we say about these shapes? The first thing that strikes the eye, I think, as I said, is that one species, Nematostella, gets thinner in the bottom, in the arboreal side, whereas the other one gets wider. And another thing is that I curvature profiles. So here it's what you can see is curvature profiles average per stage. What I realized is that the position of the minimal curvature on the lateral side, the lateral minimal curvature is actually quite constant from planula 1, and is positioned more towards the oval side in Aptasia compared to Nematostella. Now, as I said, I want to use modeling to understand where does this shape changes dynamics, this shape changing differences come from. So when I visited the lab of Guillaume Salbreux in the beginning of my postdoc, I had the chance to talk with every one of his team, and in particular, there was Diana. I could talk with Diana Koromskaya, who was actually working was actually designing a model that is perfectly suited for my project. So as I told you, the body plan of my animal is like this. It's symmetric around an axis, and it has two epithelial sheets. Well, the model of Diana, the model she designed, studies axisymmetric deformation of the sphere. So she studies shape changes adapted to the symmetry of my animals, of Cnidarians. And also, this is a model that is designed for epithelial morphogenesis. So in particular, the tissue, the model tissue is elastic with respect to area changes, resist bending, and is free with respect to shear. This is, so to go a bit more in details. So yeah, I just go back to mention that they published a preprint version of the model a bit more than a month ago. If you want to take a closer look, because I will just do a brief introduction of the model today. So this is a continuum description of the epithelium. These characteristics of epithelia, elasticity, bending resistance, and fluidity with respect to shear are associated to some parameters. And these are the constitutive equations of the model. So there is a tension tensor and a bending moment tensor. So there are many parameters in this model, but what Diana and Guillaume are focused on in this work are the implications, the roles of the parameters in red here, which are the active contributions, namely the internal tensions and torques in the tissue, but also, excuse me again, I need to, yeah, I have a little issue, okay. So the tension and torques in the tissue, and also are included the nematic components, which stem from the in-plane orientations of cytoskeletal elements within the epithelium. So today, I will mainly focus on this parameter, zeta C, which is in the bending moment tensor. And so zeta C is the isotropic bending moment. So what is the framework? I mean, how did Diana and Guillaume study these deformations? They do like this. They put an active region in the bottom, which in this case has an active bending moment, an active torque, and a passive region on the top in the blue. And by putting different extents, different patternings between this blue and red region, active and passive regions, and different intensities of the active contributions, they did simulations and established these morphospaces. So as you can see, by varying the extent of the active region in red, so on this axis, or the intensity, we have a lot of different shapes. When we go beyond this bifurcation curve here, we have also changes in topology. I wanted to mention that. So for instance, here in the square, we have a constricting neck, so the shape divides in two. Or when we are in this circle here, at this position of the morphospace, we have a curling of the active port in the bottom until the two poles intersect. So large isotropic active bending moments can lead to changes in surface topology. What I want to emphasize in this figure here is that the higher extent of this active region, this aberral active bending moments, can invert the width profile. Namely, we can go from a shape that is thin in the bottom side to a shape that is wider in the bottom side. And that is reminiscent of what we observed, what I observed between my larval shapes, planular shapes. So I want to test this. Yeah, I've been testing if these simulations were relevant in the biology of my animals. So how can we do that? There are several works that that show that using the phosphorylation of myosin is a good proxy for for tension, and in particular the differences between the apical and basal phosphorylation of myosin could be a good proxy for active bending moment. So I'm just citing this work from the lab of Guillaume Charras. So they have an apparatus like this. So in red, it is a layer of cells and DCK cells, which sits on top of a collagen layer. And when the cells digest the collagen, as you can see, the tissue will bend. They showed, and just briefly, they showed that this bending, for this bending to occur, this curling is driven by apicobasal heterogeneities in myosin phosphorylation. So if they block by a ROCK inhibitor, something that is upstream of controls the phosphorylation of myosin, if they block these apicobasal differences, the bending does not occur. Actually, they also mentioned that with this apparatus, by measuring the force that is necessary to keep the layer straight, they can estimate the active bending moment. So I use the same method, namely it is just an immunochemistry of phosphomyosin to estimate the active bending moment. So this is an illustration in aptasia. You can see that phosphomyosin is expressed in both apical and basal layers. And in this case, the bending moment can be approximated just with this formula. This is a product of the thickness of the layer times the differences between apical and basal tensions. So what I did is I just carried out here just 3D views of the myosin immunochemistry, where you can see the basal side and the apical side. What I did is just I repeated the same kind of experiments with the same antibody against phosphomyosin across across the gastrula to planula transition in both my species. And I'm interested in these three parameters I put here: H, gamma A, and gamma B. So in this cross section, you can see first that the thickness of the layer evolves. The elongation of these animals is marked by a lateral thinning of the ectoderm. First, the profile is quite homogeneous, and after, the layer gets thinner in the lateral side, like here. What I want to say is that in aptasia, this thinning of the ectoderm is shifted already. It gets thinner, more towards the oral side compared to nematostele. Regarding the basal side, the intensity is actually quite homogeneous, quite constant across the whole axis. So I just realized yesterday I had an issue with my quantification. You will have to trust me on this one. But regarding the basal side, gamma B here, it's constant mostly across the whole axis. There is some small enrichments in the oral side, but very late. For the last parameter, gamma A, here I put now full projections. As you can see, it is not constant across the axis. It's not homogeneous. There is an enrichment in the arboreal side. This is more, you can see it's more intense in the bottom. It could, the extent of this arboreal the extent of this arboreal region is is larger in Uptasia, and sometimes it goes very large. Sometimes I have some late granulas of Uptasia whose phosphorylation of myosin goes very high and takes more than 3/4 of the animal. So here are a few quantifications. And here, yeah, at planula 2, you can see that Uptasia in Uptasia in orange, this arboreal region with more intense phosphorylation of myosin is more extended. So in conclusion, the torque, the active bending moment, is located. There is an active bending moment located arboreally and in a wider region in Uptasia compared to Nematostella. However, we could not predict these shape changes from the gastrula stage. At gastrula, the thing is homogeneous, both for thickness and the apical intensity of myosin phosphorylation. So my message here is that I could not have predicted the resulting shape changes from the analysis of the initial stage, the spherical stage. So I wonder, my question now is, could we predict these shape changes, differences from the spherical stage? So what I did is that I looked at gene expression to see if it foreshadows anything. So a lot of work has been done about the genetics of this animal. I'm showing here a diagram from a very recent paper. We did a very huge work to describe the patterning on the oral arboreal axis of Nematostella at gastrula. And I selected 3 genes here, FOXA, Win2, and 636. And I repeated these experiments, but I did it not only at gastrula, but across the whole dynamics and also in both species in Uptasia. So I've been very happy last year to carry out this new technique of in situ. So until recently, it was really hard to combine different in situs to see different genes expressed at the same time. But with this new technique called HCR, so hybridization chain reaction, we are able to co-stain, to stain several genes at the same time. So this is a repetition of what you saw before, the 3 genes together. Across the whole dynamics, you can see that they stay expressed in different domains. Although, what I think is that Asia is more. So I show you quantifications because that's what interested to predict something from the spherical. Here, 3 genes in both species separately. And if I focus just on, you can indeed these 2 main already. Yeah. So this, we can combine this gene expression and then can you still hear me?
Yeah, now we can. We lost
okay.
For a couple of minutes.
A couple of minutes? Oh, I'm sorry. I'm sharing again.
Yes, you are.
We stop at HCR. Here?
Yep.
Okay. Can you hear me okay now?
Yes.
I hope it will be good.
Yes.
Okay. So I resume. My message here was that We have genes that pattern the embryo into distinct domains in both species, but the red region in the bottom is more extended in aptasia. And so, yeah, we can combine these in situs for gene expression with the immunochemistry for myosin to see that indeed the blue region, Win2, is associated to low phosphorylation in the apical side. So the blue region foreshadows a low active bending moment, a low torque. Here I just show joint quantifications to confirm that. You see that when Win2 is highly expressed, myosin is the phosphorylation of myosin is low, and vice versa. So to conclude, at gastrula, so from the eggs to gastrula, the animals, the embryos are mostly spherical. We have a gene, the patterning at gastrula differs between both species. The red region in the bottom is more extended in aptasia. And this red region foreshadows an active bending moment. And so I hypothesize that this fits the simulation of Diana and Guillaume's model, and that could explain the fact that one is thinner in the arboreal side and the other thicker. I also mentioned that I emphasized the fact that the minimal curvature is positioned more already in aptasia, while in this simulation, the minimal curvature is mostly located at the junction between the active and the passive region. So that would fit too. So to go further, to test further this hypothesis, so what we try to do is to transform one animal into the other, basically, to transform the shape, through genetic manipulations, to make nematostellar larvae look like an aptasial larvae. And for that, we use what people hypothesize as a gene regulatory network. And by knocking down some genes, we can shift the boundaries. I show you just one or two examples. So this is a normal case, the control. This is how 636 is normally expressed in nematostella at gastrula. Well, by knocking down a gene, SP69, we can move this boundary more up to go closer to aptasia. And they showed that we still don't have a wider arboreal side, but we mostly equalize the width profile. I will do much more of these, repeat and do much more of these experiments when I go back to Heidelberg. Because we know, for instance, if we knock down two genes at the same time, that we can move this boundary even more up. What I still need to do, and I didn't talk about it because of time, is that the model also comprises nematic parameters. So here I show you simulations when we just put a nematic tension in the red regions. And as you can see, we have, it corresponds to an elongation or a flattening of the embryo. So I need to describe more the nematics, which can arise from many components of the cytoskeleton. But I just mentioned quickly that at the first stages in both species, the shape of cells is mostly oriented orthogonal to the axis of symmetry. So that corresponds, that fits with an elongation of the embryo. So there is a lot of work to do, because also the microtubules can generate nematics. And as you can see when you look at them from the poles, we have different kind of orientation. So here we have an aster orientation from the arboreal side. I need to describe this more finely, because I realize that the late stages, it's very dynamic. I just show you quickly, I think I took already too much time. So simulations for the nematic bending moment this time, so which can arise, for instance, if you have different orientations between the apical and the basal layers. And I will just finish by saying that we aim to understand what is the link between the shape and the behavior of the animals. So in this case, the swimming behavior of the animals. So yeah, I want to thank all the members of my teams. So I work mostly in the lab with the lab of Alba Dismuñoz. I mentioned Guillaume Salbro and Diana Koromskaya, who did the modeling. And I want to say a huge thanks also to the lab of Annika Gus and Sébastien Rupp, who hands me the Aptasia embryos that I showed you today. And thank you for your attention. I hope my connection was not too bad and the cut in the middle.
Thank you, Richard, for the very interesting talk. Are there any questions? Yes.
Thank you for your talk. So I have a question. Actually, I find it very interesting that you somehow try to link also this wind signaling to mechanical changes, because this is what we predicted via modeling for Hydra symmetry breaking and pattern formation. But do you have any clue how wind is influencing this myosin on all this stuff? What is the connection?
Honestly, I understand very little so far. So I'm looking again at the diagram. Yes, here. Yeah, so it's known that winds travel from the oval side, which is the site of gastrulation, until the aboval side. And the last wind expressed is wind 2 here. I just observed that in the wind 2 domain, we have the ectoderm that gets thinner and the myosin that gets less phosphorylated in the apical side, but I have no idea so far about the mechanism of action of wind 2 compared to these other winds here. So I did not mention
is wind
it.
2 specific for nematostella, wind 2? Because wind 3 is very typical for development, like also in Hydra. Yes. And wind 2, I have never heard of wind 2, so it's specific for nematostella, do you know? Okay.
Yeah, so it's very interesting, I think, to look at the evolution of these genes across different species. Indeed, Win3 is very important in Hydra and in other species. Also, I showed all the hydroids, all the medusozoans I showed in the bottom. Win3 is very important and is patterned. There are some works like this. But
because I can tell you my hypothesis. I think that wind influence mechanics through beta-catenin. So I think it's beta-catenin and not wind, and beta-catenin is downstream, yes, from wind. But okay, we can discuss it another opportunity, maybe in Heidelberg.
Yeah, I would love to. I don't know. So beta-catenin, I understand that it's upstream. And so, but yeah, the winds, different winds will have different implications about the phosphorylation of myosin and the active bending moments. I can also I showed you these two species that there is a shift already in Aptasia. Wind 2 stops, is more oral. And when I designed my probes for the Institute, I realized that wind A, you can see here in gray, is absent in Aptasia. So that may explain an oral shift and all these oral shift I showed you today. I would be happy to discuss it further.
Okay, thank you very much, Richard. Is there any online question?
So there is a technical question here. If you consider the nematic order at the end, the symmetry will be broken. How realistic is the axisymmetric assumption?
You say the nematic order at the end? Can you?
If you consider the nematic order at the end, what does it refer to?
What do you mean at the end, Benoit? Excuse me.
It's a question on Zoom, so I cannot.
Okay, sorry.
At the end of the talk.
If
I think it's referring to the fact that at the end you were showing some rod-like cells, if I'm not wrong, Axel.
At the end, so yeah, I heard you badly. So I understand that the symmetry of this axis symmetry, the cylindrical symmetry, implies that we have topological defects at both poles, +1 topological defects, which can be mostly asters like this, or vertices, the vortex. I don't know what you mean by it would break.
I don't know if you hear me. Is it? I mean, if you assume this axial symmetry, then it's probably true. But wouldn't it be much more natural to have like +1/2 defects if you don't force this?
I will need to. That's a great question. So yeah, I honestly need to read more about the dynamics of topological defects, etc. But what I understand is that, and I think it's the only constraint that Diana put in the model, is +1 topological defects at both ends, which can be actually, here are the two extreme cases. So it can be a +1 like this, which can be an aster, or a vortex like this. But this is, so yeah, that's why I put going further, because I like a fine description of the nematics at the pole. It's actually quite challenging to orient the embryos at the poles at this stage because of gravity. You know, my embryos are between a slide and a cover slip, and when they are elongated, they will tend to fall. This is the kind of things I will do as soon as I get back to Heidelberg, to manage them to. I have a technique now to manage them to fit vertically like this to image them at both poles.
Okay, thank you very much, Richard.
But I think the only assumption, the only constraint they put regarding nematics is +1 topological defects at the poles.
Okay, thanks a lot. I think we should move to the next talk in the interest of time. Thank you again for the very interesting talk. Thank you. Okay, in the meanwhile, let me introduce our next speaker, Florence Aubert from Marseille, who will be talking to us about microtubule, a key target in oncology, mathematical modeling of anti-MT agents on cell migration. Thank you, Florence.
Thank you. Anna Barloukova and Rémi Tesson. So I will address the problem of microtubule targeting agent, and we will see a couple of issues about these chemotherapy drugs. So why microtubule targeting agents? It's because microtubule play a crucial role in many biological processes, in particular in cell division, but also in intracellular transport. And if you look at the right side
on the video, you see that these microtubules are filaments that are highly dynamic, and these targeting agents will perturb this dynamics and induce perturbation in cell division when they are given high dose. So at high dose, microtubule targeting agents are known to be chemotherapeutic drugs. But in fact, what is interesting for us, and especially for Stefan, was to understand what was the action of this drug at low dose, because they observed that this drug had an anti-angiogenic effect. So if they address the drug to endothelial cells, they observed that there were a reduction of the migration, and they also look at other cells on epithelial, on glioblastoma cells, and they observe for these cells an anti-migratory effect on the cells. Small effect, but at least minus 20% less of migration. So the question of Stefan was how these drugs can have such an effect at low dose, and are we able to model this effect on the migration? So the mathematical issue will be describing the dynamical instability of the microtubule, and to address the problem of modeling the effect of the drug, and also look at the problem of cell migration. Okay, so I will start with the problem of description of the microtubule instability and the action of the MTAs, and then we will see the problem of describing the action on cell migration. So what are the microtubules? Microtubule is part of the cytoskeleton characterized by the stability. So on the left, you see in the cells the family of microtubule with lots of activity. And on the right, you see a cartoon where you see one filament of microtubule. These filaments of microtubule are long cylinder of diameter 25 nanometers. And these tubes are made of about 13 protofilaments. And each protofilament is just an assembly of alpha-beta tubulin dimers. So the assembly has a plus N and the minus N, and the assembly is always alpha-beta, alpha-beta, alpha-beta. The end made with alpha is called the minus end. In the cells, this end is attached to the centrosome, so it has no dynamics. But if you look at the beta end, called the plus end, this end, plus end, has a highly dynamics. In fact, these dimers are in two different energy states. One state is more stable than the other one. The stable state is called GTP, whereas the unstable state is called the GDP. And if you look at the cartoon, when the tube is open, in fact, you can imagine that the open part of the tube is a kind of stabilizing cap. And when this stabilizing cap closed, you see that the microtubule depolymerized. What is known, in fact, is that this stabilizing cap is mainly made of the stable type of dimer called the GDP. So if you simplify the vision of a microtubule, the microtubule can be seen as a tube made first by the unstable state of the dimer, the GDP, in red, in the slide, and a stable cap called the cap, the stabilizing cap of the microtubule. The main reaction that holds in this system is that we have polymerization. Polymerization is the addition of GTP, the stable one, on the cap of the microtubule. After some time, the GTP in the microtubule are hydrolyzed. Hydrolyzation is transformation of GTP in GDP. And so we have the cap. The evolution of the cap is due to two reactions, a reaction of polymerization and a reaction of hydrolysis. When the hydrolysis rate is bigger than the polymerization rate, then the cap starts to diminish. And when it disappears, then the microtubule is able to depolymerize. Depolymerization gives rise to new GDP and stable dimer of tubulin that I will call free GDP. And after some time, these free GDP are recycled in free GTP that will be able to get polymerized. So we have a cycle, and we were able to modelize this cycle. So what we have in hands to calibrate and to study this system is the follow-up in cells of the microtubule. In fact, the biologists are able to label the GTP cap thanks to end-binding proteins and green fluorescence protein. And in fact, in white here, you see essentially the GTP cap of the microtubule. And thanks to software like Plus-Tip Tracker, we are able to follow the evolution of each microtubule and to have information on the main indicator of the dynamics. In fact, indicator of the dynamics are growth lifetimes, growth distance, growth speed. With this information, we can build information what are called catastrophe frequency, either in temporal or spatial form. But we have also information less accurate, but we have information about what we call shrinking lifetime, shrinking distance, shrinking rate, and so have information on what is called rescue frequency, temporal or spatial frequency. So with this, we will be able to try to calibrate a model if the model is able to represent this macroscopical indicator of the unstable instability dynamics. So in fact, here I also show you what is called a chemograph. So chemograph is, if you look in the vertical, you have the time. And if you look at each time of the image, each line of the image corresponds to the evolution of a microtubule. So you see in white the cap, the microtubule cap. And so you see that first the cap increase. In fact, the distance to the boundary increase. So you see that the speed rate, polymerization speed rate is almost constant at the beginning. It's about the same about the hydrolysis. And after some time, you see that the cap disappears. The disparition of the cap corresponds to a catastrophe. And if you look more carefully to this chemograph, or to look carefully to many chemographs, you see that the disparition of the cap can be due either to a slowdown of the polymerization, that can be modeled by the fact that you don't have any more or not sufficiently not a sufficient amount of GTP tubulin to be polymerized, or you also see acceleration of the hydrolysis speed. And the novelty that we introduced in the PhD of Ayuna Barlukova was to take into account this, what we call aging of the microtubule. So we started from a work from Ino and his collaborator that was proposed in 2009. The model were constructed thanks to structure population models. So this is a coupling between two structure equation and two ODEs. So the population of tubulin were split in four: the microtubule in polymerization, the microtubule in depolymerization, and the free GTP and free GDP. Free GTP and free GDP can only be structured by the time. And if we look at the population of microtubule in polymerization, there are two more traits that are important: the size of the microtubule, but also the size of the cap. For microtubule in depolymerization, we don't have anymore the cap. So the population can be structured by the time and the size of the microtubule. So it was the proposition of Ino and all. And what we propose with Ayuna to better model the aging, the phenomena of aging, but also to better model the growth indicator, the idea was to add an additional trait, that is the age of the microtubule. What is the age of the microtubule? For a microtubule in polymerization, the age is the time after the last rescue. And for the microtubule in depolymerization, this is the time after the last catastrophe. So thanks to that, we adapt the model of Ino and Hall, and we can have a look to the type of equation. So here is the equation for the population of microtubule in polymerization. So we have the time, the size of the cap, and the age. The velocity of the age with respect to time is equal to 1. The velocity of the microtubule size is due to the polymerization, and the polymerization speed is linked to the number of GTP available in the system. So we take a function gamma pole that is 0 at the beginning, because if you don't have enough GTP, you cannot polymerize, and it saturates. It's linear than saturation. Then if you look at the last coefficient in the equation, you see this is the velocity of the cap. That is a balance between the polymerization speed and the hydrolysis speed. And the hydrolysis speed depends on the age of the microtubule. Then you have associated to this equation boundary layers, boundary condition. One boundary condition corresponds to the nucleation process, that is addition of new microtubule. The other corresponds to rescue event, and we have an age boundary condition to close the system. So here are the three other equations. You see that the polymerization is modeled thanks to a transport term 2. So we say that the microtubule is able to depolymerize at a constant speed. And we have in the left-hand side of the equation for V, the apparition of two terms corresponding to a rescue event and catastrophe event. And finally, in the last two equations, the equation for P and Q, in equation of P, you find a decrease of the population due to the polymerization, increase due to recycling, and again, decrease due to the nucleation term. And in the equation of Q, you see the red term is the augmentation of the population due to the depolymerization, and loss due to the recycling. At the end, if you look at the total amount of tubulin, you will see that the total amount of tubulin in the media will be conserved. Okay. So thanks to that, IUNA was able to calibrate the system and to mimic a dose effect. So here is a dose effect of Taxol. Taxol is a polymerization drug. And what she showed and what she made is to build a strategy to calibrate all the parameters of the system. You see that we have a big system with many parameters, so it was really tricky to calibrate it, but she succeeded. And on the right, you see the data, the macroscopic indicator of the instability in this graph. So here we have 4 indicators of the stability that we used: the growth rate, the depolymerization rate, gamma dipole, and the frequency, temporal frequency of rescue and catastrophe. And we put this indicator on the 4 alpha axes in the plane. So with no drug, we put this indicator to ±1, and we model the effect of the drug on each of these indicators. And what you see is that this evolution is non-monotone with respect to the dose of drugs. And here, what you see is the effect that even for very low dose, 1 nanomole of drug, you see a big effect of the drug on the frequency of rescue, for example, but not only, also an effect on the frequency of catastrophe. And so what proved IUNA is that this small effect, this effect due to the small dose, can be explained by an effect on one parameter that was RS in our model. And RS is just a delay linked to the time needed for a microtubule in depolymerization to go back to the polymerization state. And a small effect on this parameter can explain large effect on the macroscopic indicator. So we were happy to have a small possible interpretation of this effect at low dose. Okay? So here is the work we've done with IUNA, but in fact we go further with Magali Tournus and Diana White, because we were not satisfied by the modelization of the depolymerization. In fact, depolymerization the depolymerization speed is bigger, much bigger than the polymerization speed. And we can see the depolymerization process as a sudden process. And so we decided to model it thanks to fragmentation model. So we changed the equation on V here, and the depolymerization is now modeled thanks to fragmentation term, and we are still working on it, and we simplify this model to try to look at the asymptotics of this kind of things. So when we will look at the cell migration process, we will have to go further, because the localization of the microtubule will take a crucial role. And so you will see later in the talk how to build a very, very simple model of microtubule, but using the space dependency of the microtubule. Okay. So now cell migration process. So we will first look at the actors of cell migration, and I will focus on one model built by the team of Edelstein-Kechet, and you will see how with Rémi Tesson we adapt this model to take into account the microtubule impact on the process. So first here you see two movies. On the left you have a control cell, so no drugs. And on the right, you see cells with drug. This is a depolymerization agent here called vinflunine, if I'm not wrong. So you see that in that case, the migration speed decrease. You see that you have less contraction at the rear of the cells and less dynamical activity at the front of the cells. So you see the impact at low dose of one microtubule targeting agent on this type of cells. So what are the main engines of the motility? There are four. First, actin polymerization or nucleation at the front of the cells. Second, membrane tension of the cells. Then cells adhesion to the substrate. And then cell contraction. What I omit to say is that I will concentrate on migration on the 2D substrate. 3D migration is has a different type of process. So one of the main actors is the filament of actin. Filament of actin are other part of the cytoskeleton. And we see in the cartoon from the paper of Blanchois that the organization of actin can be different with respect to the position inside the cells. At the front of the cells, you see a branch cross-link network located at what we call the lamellipodium of the cells. You see also fingering of the cells that correspond to the organization of the filament as parallel bundles. And if you look at the back of the cells, you can see stress fiber that is parallel fiber, but in the other direction. The filament of actin are also polymerized with the plus N and minus N. The plus N is called the Barber N, and in the case of stress fiber, the plus N are on the other side. Okay. So these actin filaments are regulated by many, many proteins. And among these proteins, we can mention RP23, linked to nucleation and forming at the location of the filipodium. There are many proteins linked to sequestration, thymosin, frophilin, twifilin, capping. In fact, these proteins limit the polymerization of the actin, maintaining a pool of actin available, always available. There are also proteins linked to fragmentation and depolymerization. We can think about cofilin, gelsofilin, and protein linked to contractility that are mucin protein. And in fact, all these proteins are regulated themselves by Rho GTPase protein. RAG protein at the front of the cells, Rho protein at the back, at the rear of the cells, and CDC42 for the filipodium part of the cells. So, to be short, we can say that RAG protein will promote the protrusion of the cells, so promote a force that enables the cells to go further. And at the back of the cells, the protein Rho will promote the contraction of the cells. Okay? So, the work of the group of Edelstein-Keschet propose a very simplified view of this complex activity. And what she proposed is first to say that the cells is something can be modeled thanks to fluid dynamics. And this fluid dynamics, if you look at the Reynolds number associated to the cells, you can see it's very low. And so the inertial force exerted to the cells are negligible with respect to the viscous forces. And so we can look at the system as the Stokes, thanks to the Stokes equation, with U that will be the velocity in each point of the domain corresponding to the cell, but also outside the cells. And in the work of the group of Edelstein-Keschet, they say that there were two types of forces that exert on the cells. There were protrusive forces and there were elastic forces. They neglect the contractile forces in that vision of this simplified vision. So coupled to this mechanical model, we have inside the cell a biochemical model. And in the paper of the group of Edelstein-Keschet, they only consider one type of protein. You can think at the protein RAC. And this protein can be either in an active form or in an inactive form. So this protein will evolve inside the cell thanks to a transport term due to the fact that everything moves at the velocity u, diffusion process, and reaction terms that explain how the protein will be activated or inactivated. Okay? So starting from this work, we decided to improve a little bit the description of the biochemical model. So first of all, we will add the Rho protein in the system because we want to take into account the contraction forces at the back of the cells. So if you look at the Stokes equation, we have an additional term corresponding to the contractile forces. And then we also add a model that will represent the action, the presence on the microtubule. So we are not able to couple all the precision we had in the model of Ayuna here, and we decided to limit us by having a quantity that will model the amount of tubulin in each point of the cells. And we suppose that we had a certain number of microtubules, n microtubules, somewhere at the front, somewhere at the back to handle the contractility. And for this microtubule, we keep the position of the cap and the length of the microtubule. Okay? And we decided not to keep the approach of the group of Edelstein-Quéchet. Edelstein-Quéchet represent the cell, the membrane, thanks to marker cells. And we prefer to use a level set approach. So level set approach consists to say there is a function phi, and the membrane of the cell is the zero level of this function phi. Inside the cell, phi is negative. Outside the cell, phi is positive. So let's come back to the chemical model. So for the protein, we find again the same type of equation that we have in Edelstein-Quéchet. I will be more precise on the reaction term GP here. So for example, if you look at the reaction term for the RAC equation, you see that in red we have a localization term that say that we will have activation of the protein RAC only in the neighborhood of the cap of the microtubule. In blue, you have the classical reaction term that you can find in Edelstein-Quéchet, with a slight difference that it will depend on the presence of microtubule and tubulin. And if you look in green, in the desactivation term for RAC, you see that we put a competition term that say that in presence of Rho, we have desactivation of RAC. It was one of the main property that Stéphane Honoré tell us about the protein Rho and RAC. So a term that is quite near from the one of Edelstein-Quéchet, but with localization and competition between Rho and RAC. Now, if we look at the tubulin concentration, the tubulin concentration will follow a transport reaction diffusion equation. Transport to the speed u, diffusion, and with the reaction term that say that we lose tubulin due to the polymerization, and we have polymerization in the neighborhood of the cap of the microtubule. So that was, we have this delta function here. And you see that the velocity of polymerization is something that is taken here linear with a concentration, threshold concentration Cc that will play a crucial role in the effect of the direct in a moment. In fact, here you see that the depolymerization of the tubulin is linked to the parameter Cc. So we have a linear velocity, and if the tubulin is less than this concentration, the microtubule depolymerized, and if not, it polymerized. And this concentration is linked to what we call the equilibrium linked to the dynamical instability. We have dynamical instability, but we have dynamical instability around some equilibrium. Okay, and here Cc is this equilibrium. Okay, so now the position of the microtubule. We have two types of microtubule that are on the front of the cells, microtubule that are in the back of the cells, plus for the front, minus for the back. And we have a region in neighborhood of the membrane where the microtubule are more unstable than far from the membrane. So in fact, we split the population in four type of microtubule. So the evolution of the microtubule the position of microtubule will depend on the velocity of the cell U, but will depend also on the gradient of the tubulin, the gradient of the protein rack at the front, and we'll have a different orientation if we are in the front or in the back. And finally, the length of the microtubule is just linked to the velocity of gamma pole and dependent on the position of the microtubule. So, with this, we can come back to the forces that we had in the Stokes equation. We had 3 forces. One force that is elastic forces. The elastic forces took the form that we can find in the work on Côté Maître in a paper of 2008. So it depends on the level set function phi and is located on the neighborhood of the cells. Protusive forces and contractile forces are also located in the neighborhood of the membrane, and they're both oriented with the normal of the membrane. The normal of the membrane is gradient phi over the norm of gradient phi. And the intensity of the force depends on the presence of the protein rack at the front and rho at the back, with different type of shape that can be found already in the paper of Edelstein and all. So to calibrate this model, we built with the group of Stéphane Honoré a couple of experiments, and especially we had an experiment where they get either on the same cells the microtubule dynamics indicator and the migration indicator also on the same data. So these cells were either control cells, either treated thanks to vincristine. Vincristine is a depolymerization drug too, like the vinfluminine where we saw the effect in the first slides. And so we had information on microtubule dynamics after the information of cell migration, but also before them. So this is information for the dynamics of microtubule and cell migration, but we also add information about the protein rho and protein rack. They made what they called collimetric ELISA assay, and they were able to quantify the amount of protein rho and the percentage of activation of rho and rack. Unfortunately, we didn't have the amount of protein rack with such experiments. So, with this, we can look at the effect of the drug. You see that if you concentrate in the red table, after 3 hours, we have a deep effect on the migration speed of the cells. You see that if you look at the red table, you see that the cross speed of the cells decrease, and you see that the cross catastrophe frequency increase after the effect. So we try to reproduce this phenomenon, and here are the impact, the results, the output of the ELISA cells. So you see that the drug decreases the total amount of protein rho, and you see that the drug decreases the activation of the protein rack. the rate of activation of protein RAC. Okay. So here is a simulation of Rémi starting from an academic cells that is circle cells with a certain amount of microtubule at the back and at the front. And you see that the shape taken by the cells is quite reasonable. You can see here, after 3 minutes, the evolution on the left of the RAC concentration and on the right on the rho concentration. And we can also model the effect of these drugs, so these vancomycin. So what we've done is to say that the drug will increase the stabilizing zone of the drug, so the parameter which is called distab was increased, and the drug will perturb the equilibrium, and in fact will increase the concentration CC. So we increase we decrease the speed, so we increase the CC, and we can look at the resulting data. So to conclude, I show you in 2 types of example how to take into account a low dose effect of MTAs. So with a quite complex model to take deeply into account many aspects of the instability process. And for the motility of the cells, we are more rough. It's more academic model, but it was a first step for us to learn about cell migration at that time. Thank you very much.
Thank you, Florence, for the clear and interesting talk. Are there any questions? Yes, Luis.
Thank you for the nice talk, Florence. I had 2 questions. One is, in the chemograph you showed, what were you marking with fluorescence? Yeah, this, because you seem to have the signal fading out before you depolymerize. So, you seem to have that the signal that you're marking is fading out before you start depolymerization.
So when you look the pack, when you look the cap, you have a depolymerization, and so you don't see the phylum, the microtubule.
Okay.
And then you find again the microtubule when we have a rescue, when the microtubule polymerize again.
Okay. So what you're marking?
The fluorescence is only able to mark the GTP.
Okay, that's it.
The GTP.
And so you see it fading out before.
So when it disappears, you have a catastrophe.
But it doesn't seem to disappear at once. It seems to fade out. So it doesn't seem to be that discontinuous.
Yes, you have some default on the cap before. It depends on the chemograph.
Oh, okay, it's not a typical thing.
So here I choose a chemograph where you had this default to see that we may hypothesis that aging of the microtubule
makes it fade out.
Yes, okay. But this is something that was observed many times by Stéphane. So.
Okay, it's linked to the second question, which is, I'm a bit surprised that you can model this as a fragmentation process, because when you break into 2 fragments, you have that your microtubules, one of the fragments is linked to the centrosome, but the other one is free.
So in fact, I talk about fragmentation, but my microtubule fragmentation consists in a shorter microtubule with many GDP, free GDP.
Okay, so the second fragment just disintegrates right away.
Yes, the second fragment disintegrates.
Okay. No, then it makes sense. Thank you.
Are there? Yeah.
Do the microtubules, in your last part, do the microtubules interact with the cell membrane? Are they pushing on it or are they pulling on it in your case?
Sorry?
Do the microtubules interact with the cell membrane if they go all the way? No, they don't interact at all. No. They neither push nor pull on the cell membrane.
No, I don't think so. I have no...
Any more questions?
No, the force induced by the protein is linked to the fact that the protein will activate the polymerization of actin, and so it's a rough description.
If it interacts with the membrane, it could change the capacity.
Yes, yes.
Any more questions?
Where do you get the nice properties of the level sets of your function phi so that it doesn't split into different components? It comes from where?
We stopped before. The computation is very long, so we don't see
your level set splitting.
No.
But there's nothing in the equation to prevent that.
Probably, but the computation was so long that we did not reach this time.
Okay, thank you.
I do have a quick question. In the second part of the talk, you assume the functions gamma and g to be linear.
Gamma
and g at some point there were. Next slide, probably a couple of slides after.
A gamma point.
Yeah. How much do you think that affects the results? Would the results change a lot if you change the definitions for those functions, or?
If the concentration of the tubulin stay around the concentration CC, it won't change a lot.
Much. Okay.
Won't change a lot.
Okay.
I'm not sure in the model of Ayuna we see really the plateau.
Yes, yeah, I understand that. Okay, makes sense.
Yes.
Okay, thanks. Any questions on that?
So there is a question online. So the question is, you use the term catastrophe. Is it connected to some catastrophe theory models?
Catastrophe?
Catastrophe.
Alors, catastrophe is catastrophe in English, so sorry for that.
No, but is it connected to the catastrophe theory?
No, I think it's the vocabulary that Stefan used. He always, when the microtubule depolymerizes, he say it's a catastrophe.
It's not connected to the theory from the 70s or whatever.
No. It's just the vocabulary he used.
Thank you.
Thank you. We are a bit late. Shall we resume in 10 minutes instead of 15? It's okay. Yeah, we will resume in 10 minutes then. Well, okay, at least I can start introducing our speaker, probably. No.
Merci.
Okay, that's perfect. It is my pleasure to introduce our next speaker, Camille Pouchol from Paris, who will be talking to us about asymptotic analysis for some selection mutation models, location and weights of limit singular measures. Please, Camille.
Thank you, Tommaso, and thank you, thanks to the organizers for making this happen in spite of all the tests that have been necessary to make it possible. And also, I want to stress that there is an error in my first slide. It's no longer Université de Paris, so it's just an unknown entity. But you know, I had to put something right. So I will be speaking about some joint work with Tommaso Lorenzi. And this is about asymptotic analysis for some selection mutation models. So definitely this has to do with the word growth more than probably tissue here, but we'll see along the way. So what I tend to do when I introduce this subject is I tend to start from the basic logistic ODE model. Namely, you have a certain individuals. Usually I might use the word cells, N of T, and these cells proliferate. They have a net reaction rate R, and they also have an additional death rate, logistic death rate minus N. And now, very abstractly and very generally, we want to take into account the possibility that cells might proliferate according to a certain phenotype that I will call either phenotype or trait. X will be continuous. So you can think of, if we are speaking about cells, it could be, for instance, the concentration of a given protein in the cells or the size of the cells. And now the function, now the parameter R becomes a function, which is called usually the fitness function, and depends on X. And certainly the easiest way to generalize the previous basic ODE model is to replace this function R by R of X. That's the first thing, but then you need to say what you do with this logistic additional death term, which was minus N earlier. And the simplest way to go about it and to describe the evolution now of a density of individuals N of Tx at time t and of phenotype X is to put the total number of individuals rho of T, what I usually call blind competition, because this means that a given individual of phenotype X is in competition with all other phenotypes independently of their respective phenotypes, which is very different from what you would expect. For example, if X represents space, then you would expect that there is some kind of local behavior rather than such a blind competition. So this is really the simplest way to go about it. So X ranges over some set omega, which is a subset of RD. And the questions that have been posed, especially in this context of adaptive dynamics, where you want to understand which phenotypes will take over, will be selected in the population, is to first try to see what happens in terms of asymptotic behavior of the total population rho of T. And then secondly, although the first one can be subsumed in the second, you want to look at the phenotypes that are selected at the end eventually. Namely, you want to look at possible limits of the density as time goes by in the set of measures. We'll see that this is the right set to consider. And a general, relatively easy result to establish once you have the right idea, which you can find in Benoit's book, Transport Equations in Biology, is that what I like to call convergence and concentration is that the total number of individuals rho of T converges to the maximum of the function R, and what could be considered as non-surprising, the density of cells, n of t, concentrates where R reaches its maximum. In particular, if this set happens to be reduced to a singleton, this means that the whole population will concentrate on a given specific one single phenotype with the correct weight, namely Rm. And the questions that we were interested in with Tommaso on this subject was to investigate the situation where you have several phenotypes that maximize the fitness function. And especially related to what is known to be difficult in this area is the question of polymorphism. How can you have several phenotypes that simultaneously take over and are present in the population? So here now we assume that the maximum of R is reached at n points, n larger than 2. And also kind of related to the first question is that of the speed of convergence of different quantities to the respective limit. And the best estimate we were aware of at the time is the following, which was established by Pierre-Emmanuel Jabin and Gaël Raoul. I think it's the first time I talked about this in front of Pierre-Emmanuel Jabin. I've been saying Jabin and Raoul a lot of time, but never in front of you. So the result is the following, is that you know that the rho converges to its limit, so maybe you could forget about the second term for now, this term. But the first term tells you that rho converges to its limit at least as fast as log of t over t, which is quite slow. So you could expect maybe you've lost something in the process and it's exponential. What Jabin and Raoul have proved is that in fact it cannot be faster than 1 over t to the power alpha for any alpha larger than 1. But still the actual speed of convergence is elusive, was elusive at the time up to our knowledge. And another related question is, what is usually done in the field is to add mutations to say that, okay, individuals proliferate, but the mother cells will give birth to daughter cells that do not have exactly the same phenotype as the ancestors. And one way to take that into account, one rough way, is to add mutations, or I should say genetic instability for Jean. Namely, to say that individuals will change phenotype over generations, slowly but surely. And we also add Neumann boundary conditions. So this PDE now, it's a non-local PDE, has the same reaction term as earlier, R of x minus rho, but it has also a mutation term that actually couples. So earlier we had an integral differential equation because the phenotypes were uncoupled, except for the non-local term rho. Now they're also uncoupled because of the diffusion. And the question is now, you can look at the, let's stay here. You can look at the asymptotic behavior of the PDE. And then, once you've established, you can look at the stationary states that you've reached. Let beta go to 0. So in other words, you're interested in interverting limits. So first you can look at the PDE, let t go to infinity, and then let the mutation rate go to 0, beta go to 0. Or you can do the opposite. First, let beta go to 0, which means at least formally this model boils down to the integral differential one where you had no mutations, and then let t go to infinity. These are the questions we're interested in. Of course, this is linked to works by several authors, some present in the room, Benoit and Cepide and Cepide Mirami and some others, where you change timescale, assuming small mutations, and then you can follow the selected phenotype, assuming concavity. So for those who know, is obviously quite linked, different but complementary to these works. Okay, so let me start with the integral differential equation. So you have this, the first model that I've introduced, and you have the function R reaches its maximum. So there's possible polymorphism. There are several best phenotypes that have the highest reaction rate, and we're just assuming that the maximum points of R are non-degenerate. And the result that we've established with Tommaso is the following, that we can completely characterize the limit, namely that we knew earlier n of t concentrates on the set of the xi's, but you can actually compute the exact weights that you have in front of these xi's. And these weights, they involve not only the value of the initial density at the xi, but also the Hessian namely takes into account the local concavity of R near the maximum points. And the second result that we've established is related to these questions about speed of convergence. Namely, we proved that rho, the total number of individuals, converges to its known limit at the speed 1 over t, and the constant is d over 2, and d here is a dimension. Okay. So what is the idea of proof? So essentially, we start from the implicit formula that's here, and it's just because the model is completely exponential, so you can solve it implicitly because, of course, you don't know what rho is. You could actually solve it explicitly, completely, but it's not a very nice formula to deal with. And then, once you have this, and you want to look at what happens at the level of rho to start with, you can split the contribution of the integral of n of tx over the domains, over small domains, small balls around the maximum points. And this allows you to use the Laplace formula. Laplace formula tells you that this integral, where f is some function, will essentially be dominated by exponential times where r reaches its maximum times t. So this is the term here. And there are correction terms, not only in terms of the local concavity of the function r, but also in terms of the time variable. So there's a t to the power d over 2. And when you combine these estimates and use compactness, because to start with, you know that there are subsequences that converge, and you actually establish that there is a unique possible limit, so you know the full trajectory converges to that. And this gives you the first result. And for the second, unsurprisingly, you need the next term in the expansion of rho. You need to use asymptotic expansion given the Laplace formula, so you need a better Laplace formula that you can find in literature that tells you how this integral can be approximated at the second order. And then you can actually prove this result. So a couple of remarks. The first remark is that it's very different from what you would obtain for the corresponding ODE. So recall, if you look at the ODE, the logistic ODE, which can be solved explicitly, you have exponential convergence to the limit. Whereas here you have a much slower convergence. And it's even stronger than this in the sense that this simple integral differential equation contains the logistic ODE if you start from a Dirac mass at a given point. And it also contains systems of ODEs where you would start from the sum of Dirac masses, where you can also prove that exponential convergence towards the global asymptotic stable equilibrium holds. So because you go into continuum, you go from exponential convergence to very slow convergence at the speed 1 over t. Another remark is just to make the remark that the first order is universal. You could expect that for here you could have something that depends on the function r or on maybe the initial condition, but it's not the case. You get this universal d over 2 constant. And also it depends on the initial condition, so that's more, that's about the limit of the density. Here the initial density appears, n0 of xi. And this shouldn't be surprising because, again, if you look at this implicit formula, the limit of n of tx has to scale proportionally to n0. So this is quite natural. Okay. So just one simulation to highlight the results. So we have here is the R function that we use that has two maximum points, one at minus 0.5, one at x equal 1. And you see that the concavity of R is somewhat nicer near 1 than it is near minus 0.5. And if you let, these are simulations made by Tommaso, if you look at what you obtain in terms of the density, so here is time, and here is the phenotype. You have to, this is flipped, so be careful that here is 1 and here is minus 0.5. You see that as time goes by, and as predicted by the theory, you should have mass both at minus 0.5 and at 1, and you do. And also, this shouldn't be, we start here from a constant initial condition, and you see that the masses are different because there is this Hessian playing a role telling you that there will be less mass where R is not nicely concave enough. And rho converges, and we could not prevent ourselves from checking that, well, first, this is to tell you that the weights that we are finding theoretically are recovered numerically on the left. And on the right, we could not prevent ourselves from checking this d over 2. So when d equals 1, d over 2 equals 1 over 2. And indeed, you find that the limit of rho minus rho times t converges to 1/2. So this is all works fine. Now let me move to the case of the PDE. So now we add mutations, and we are in the world of non-local PDEs. And here, what's appropriate to look at the asymptotic behavior is the expansion of a given operator in L2, namely the operator beta Laplacian plus R. And I will denote its principal eigenpair, so principal eigenvalue lambda beta and principal eigenfunction psi beta. And this is, I normalize psi in L1 because this is, we are going to integrate densities, so this is a good way to normalize. So here, partially, this is based on a technique that has been used. For example, you can find this technique used in the work by Hélène Le Mans, Sylvie Mellard, and Sepideh Miraimi. And we use the technique, we go a bit further with the technique to get speeds of convergence. So the result is as follows. If the first eigenvalue is non-negative, then the total number of individuals goes to 0, actually exponentially. And if it's negative, then it also converges exponentially, but this time to minus the principal eigenvalue. And the density converges to a multiple, here is a multiple of the first eigenfunction. So the idea of proof, again, the idea of proof is not new. The first thing to do is, essentially, the PD here is almost linear. Only this embarrassing quadratic minus rho beta, but it's just something you can get rid of by an exponential change of variables. So if you change variables by not looking at n, but by looking at another density that's given by w times n, and w solves a properly defined ODE, then you get an equation for the new density that's completely linear and has 0 eigenvalue as the first eigenvalue. So then you know that you can just expand it on the basis that u converges to a multiple of the first eigenfunction, and then you can go back to the initial density that you were interested in and get the result. And then you need to go to the next order in the estimate to get the speeds of convergence. And in fact, you can prove that the convergence is exponential, and the rate of convergence is governed either by the first eigenvalue or by the spectral gap of the operator. Okay. And now let me move on to the last question, which was, can we, how do the limits compare in terms of the PDE and the integral differential case? So for the integral differential case, we know that rho converges, that the density concentrates on the support on the maximum set of R. And in the PDE case, we know that rho converges also if the principal eigenvalue is negative and the density converges. So now the question that I asked earlier is, what happens when beta goes to 0? And when things commute means, if you just look at a few first results, it seems like things do commute completely, you get the same thing. And then when beta goes to 0, the convergence, there is convergence of minus lambda beta, so the limit of rho beta to the maximum of R, which is what you would expect if things are supposed to commute. And also, the first eigenfunction of the operator also concentrates on where R reaches its maximum. So this is all in perfect agreement with the integral differential case. So in particular, again, if you're in the specific case where R has a single maximum point, then the limits completely commute. The density of the integral differential equation converges to a Dirac mass at this point with the correct weight, and so does the limit of the PDE when beta goes to 0. Just one remark is that you can also get this result that the limit commutes if you have sufficient symmetries, namely in both the fitness function R and the domain. Okay, and the proof of this is to use the variational characterization of the first eigenvalue and to test it against suitable Gaussian function that will converge to Dirac masses near maximum points with the correct variance here. So if you test that with some exponentials, you really get a fine estimate of lambda beta. And once you know convergence, once you know that the principal eigenvalue would converge to minus Rm, then concentration follows from using this basic identity, which is just consist in integrating the PDE, the elliptic equation satisfied by psi beta, and then passing to the limits. Okay. And now, this is where things are a bit more surprising, and this is given for free in some sense by semi-classical results, semi-classical analytic results. Now what happens if R has several maximum points? We know that in the integral differential equation, somehow the limit remembers the initial condition. It does depend on the initial condition. But we know in the PD case, there is no way that such things happen because the limit is completely independent of the initial condition. And this is reflected in this result that tells you that the principal eigenfunction, whenever there are several maximum points, will concentrate on a very specific subset of the maximum points. So here is a bit of a complicated measure of concavity of the function R at a given maximum point. The formula itself is not interesting, but it tells you that there is one way to measure the concavity of R that will tell you where the principal eigenfunction will concentrate. It concentrates on Argmax of R, the maximum points of R, and inside this set, it will concentrate on a very limited subset. In particular, if this subset is reduced to a singleton, then the first eigenfunction will converge to a Dirac mass. And again, this is actually a direct application of semi-classical analysis result, where you have to in semi-classical analysis, you have a double well typically, so you have a function like this, and you want to look at if you have small noise. You want to know where the particle will land, and semi-classical analysis tells you that if you have something that's a lot smoother here, then the particle will eventually end up here in the limit of small noise. And in the case of adaptive dynamics, with our fitness function, you have to look at things this way, and this is the fitness function is like that. And it's also possible to narrow down further the concentration set, but the notations are cumbersome. So if it happens that the set argmin of psi has several points, then you can go further in this business. There are also some results that you can find in some works by Sepidemi Raimi, where using approaches of Hamilton-Jacobi flavor, you get also expansion for first eigenfunction, especially actually first eigenvalues, and it's a perspective to recover these kind of results using these techniques. And I'll just end with a few simulations. So this is the simulation you saw earlier with this function R. And in the integral differential case, everything at the limit you had mass both at 1 and minus 0.5 here and here. And now if you do the same thing with the PDE, but with a very small mutation rate, so here beta is 10 to the minus 6, then you should converge to a multiple of the first eigenfunction, and you know that this first eigenfunction is localized only where R has the smoothest concavity, so namely at the point 1. And this is what you see here. And there is a transient behavior, which could be analyzed by different techniques, where you first have kind of mass both at both points, but then in the end, all the mass goes to the point x equal 1. So this is also in perfect agreement with the theory. And I'll stop here. These are some references linked to my talk. Thank you.
Thank you very much, Camille, for the very neat talk. Are there any questions or comments? Yes.
Thank you. It's actually you just touched on that, right? When you talked about this transient behavior, is there any way to characterize the time scale of this? How long, if beta is very small, so how long it would be close to the two maximum, and then
Well, I think that's related to the kind of approaches that I've mentioned here.
Yeah.
So here. So you would expect that you have this kind of behavior. So I don't know if the theory here with such technique from Hamilton-Jacobi equations has difficulties treating the case of polymorphism. So I would expect that you get the same kind of timescales, which is to take here beta. Sorry, square root of it should be square root of beta if you get the runtime scale here.
Yeah, but this is a little bit of a different scaling. The second one.
Yeah, but I mean, still, I don't think we checked exactly the correct scaling in terms of beta. I don't remember, but. So I cannot say if there is something very funny appearing, like there's a surprising exponent to beta that comes in. Certainly there is one, but I don't know if there is a specific phenomenon linked to the fact that you have this polymorphism. But I couldn't say more than that.
Okay, thank you.
Any more questions?
Yeah.
Is going to be very different?
Well, what we found in these papers that it doesn't change things apparently, which also surprised me. Actually, I had an exchange by mail with Helfer about this, the passage from L2 to L1, and he said, no, you'll get the same thing. But I agree, it's not clear. Also, there are some works by I forgot his name, but. Where things are done in L1 also, and you get the same measure of concavity appears. Yeah.
Okay, I think we can stop here. Thank you again for the talk. Can you hear us?
Yeah.
Brilliant. Okay, so we can move to our last talk of today, which will be given by Monika Piotrowska from Warsaw, who will be speaking to us about computational modeling growth and response of multicellular EMT6, RO spheroids to multifraction irradiation. Please, Monika.
Thank you. Good afternoon. First of all, I would like to thank organizers for inviting me and giving me opportunity to be here. I mean, be here online. Let's start. I hope you see it. This is okay? Okay. Few words about the motivation. As probably you know, most of people receive radiotherapy during their cancer treatment, and it might be because it might be the first choice therapy, or it might be a palliative treatment. And majority of the schemes used in practical use are low dose fractions applied twice or once a day, excluding weekends. So you receive your radiotherapy only for 5 days, and then you've got a weekend break. And so the national question would be to explore the possibility of finding better protocols, and maybe because of timing or dosage or both of them. And here you've got standard protocol visualization. So it's a standard 10-gray protocol. Patient receives 8 times 1.25 grays. And if you consider that that's the 10 fraction program, and you allow some kind of restricted time gaps, like, for example, 18 and a half up to 30 hours, then you can easily calculate that you got 55 trillions if you use short scale, and if you use long scale, it will be 55 billions ways or different protocols. So, so the question is, can we find a better protocol? First, our first approach was by changing only the timing of the doses, but the natural consequence would be also to focus on possibility of changing fraction and dose at the same time. And so here's the presentation of 2 benchmark protocols, and I will call them benchmark because there are 2 standard protocols used in clinic. So the benchmark one, first one, it's 1.25 grays given twice a day for 4 days. So the total dose per week, it's 10 grays. And the second benchmark, it's 2 grays given daily for 5 days. So both of them gave the same amount of radiation. And what we see in the picture is a fraction of cells of tumor cells in different phases, G1, S, G2, and plus M2 put it together. And the hypothesis is that first radiotherapy induce some kind of synchronization of cell phases for the cells that create the tumor. And second would be, can we hit the cells in proper phase at the right time to increase the efficiency of the protocol? So basically, this presentation it's a story of my collaboration with Simon Angus. So Simon Angus is a researcher at Monash University, Australia. And I met him in 2007, I guess, when we both were PhD students. And he was not so much familiar with the cancer modeling. I was not so familiar with practical usage of serial automata. So that made us a perfect scientific couple for the collaboration. And so we decided to think and work together. And as you can guess, we didn't met in Europe or in Australia, but we met in United States during the workshop. Or rather summer school organized by SFI, Santa Fe Institute. Okay, so our goal was to check if we can find better protocols, but to do that, we first need to have like high fidelity model. And at the time, I consider myself more like a differential equation person. So for me, these numerical models or computational models were some kind of challenge, so the first step was to establish the model itself, so just to consider the tumor growth, and we published the results in 2009 in JTB. And then we introduced the response to single-dose irradiation, and it was another paper in JTB published in 2013. And after that, we said, okay, I mean, we've got the single response, but what about the multi-dose irradiation? And actually, our aim, so our goal was closer, that we can search for better protocols. And it took us a while, and we published our result in +1 paper. So it's a very long paper with huge supplementary materials, but I recommend it. And the last step, it's recent current work when we instead of considering multi-fixed dose. So in this +1 study, we fixed the dose, and we only play with the timing between the irradiation events. But recently we also consider protocols with some restriction on a dose, total dose, or a single dose, but they were not fixed. That work was due to collaboration with Wojtek Ozimek, Rafał Banaś, and Paweł Góra. And I will acknowledge them at the end of the presentation. So, okay, so what about this model? So we wanted to have a high fidelity model just to be sure, or to have highest probability of the translation to the clinical lab. And we focus on a single cell line, EMT6RO. So it's a mouse mammary tumor cell line, and it's analog of human breast cancer. And we choose that cell line because we found a lot of literature about this cell line. And yeah, and so the goal is to find a better protocol. And so where's the cellular automata? So what's the approach we used? So it's a computational model when we consider grid. In our case, it's regular grid. And we define the rules for cells to divide, die, and die of different reasons. And everything it happens at the microscopic level, and macroscopic level we observe the result. So we consider the lattice type, which we called quasi 2D. So it's something between 2D and 3D. And it means that instead of considering single cell in each position of the regular grid, we consider a package of cells. We directly model nutrients and waste, so the glucose, oxygen, and wastes, understood as H+ ions. And the fate of the cell, of package of cells, is determined by the concentration of nutrients and wastes, of course, cell cycle of the cells, cell metabolism, and of course irradiation. Okay, so shortly about the cell cycle. So as you guess, the cells prefer to proliferate. So they go through the different cycle phases, G1, S, G2, and M. And they can get quiescent of because of some reasons only in G1 and G2 phase. And whenever the new cell is born, or meaning that the cells divides, the new cell gets its own cell cycle duration, and it's because it's got its own G1, S, G2, M, and D phase duration. So at the point you already see that it's a stochastic model, And also the placement of the cells when they divide is also stochastic. So we've got different types of stochasticity in the model. So maybe I will not go too much into details. And the main idea of the metabolism of a cell is that cells prefer to proliferate than be quiescent, and everything depends on the environment. So if there's not enough nutrient, not enough place, they will die. They can proliferate in anaerobic or aerobic way. So it means that anaerobic, it's when the cells got not enough oxygen to proliferate in a normal way. So it can switch to anaerobic and adjust to anaerobic conditions and consume more glucose and do not consume oxygen. Okay, so because we wanted to have like high fidelity model, we needed to calibrate it at multiple stages. So as I said at the beginning, we work only on a model of tumor growth. So JTB 2009 and 2013 papers. So we had reference data set of papers by Fryer and Sutherland. And we've got a lot of objective functions like growth rate, saturation size, necrotic core formation, size of a necrotic core, and so on. And we managed to find a lot of parameters in the literature, biological literature, but we had a problem with one particular parameter, meaning a diffusion coefficient for glucose. And it appears in literature that there is huge differences between the reported values. And as you see here at the bottom, that there are the difference of order of magnitudes. So, so we use this diffusion and other objective function to find a diffusion constant, which will allow us to get to replicate the experiments, biological experiments, when tumors were grow for 20 days at a given substrate medium. So in particular, 5.5 millimolar glucose and 0.27 millimolar of oxygen, and at given pH, it was 7.4, I guess. Okay, and then we had our model, and we managed to get like the good agreement with the final diameter of tumors, diameter, growth rate, necrotic onset, or onset of necrosis. So the size of the tumor when the necrotic core is formed, estimate doubling time, saturation volume, and the cell count. And here's another one. So it's like thickness of the variable rim. And for the simulations, we've got the markers, this closed markers, open markers for the data from the literature. And we see that we are quite close to what was reported, once again, repeating the given experiments. And the next step was to introduce the irradiation. So we got another reference data set, and because it's a stochastic model, so there is a quite simple rule, so that we didn't know the probability of death and the delay of the repair. And as objective function, we use percentage of the zero volume for 3 considered radiation doses. So, so of course, there is no such a thing like immediate cell death upon irradiation, and we assume that the cells undergo repair at checkpoints, excluding one when there is a transition from mitosis to G1 phase. And we assume the repair takes some amount of time, and it depends on the dose received by a cell, and of course the repair is not always successful, and so with some probability cell will survive or will die, and this probability also depends on R. And to find those two unknown parameters, we focused on the experiments performed by Kelly et al. So they inoculate tumors, and they at day 0, then at day 2 they apply irradiation, and they follow the volume of growing tumors along the time. So what we done, we check different values of delays and probabilities, and minimize the error. And it's not a standard mean square error, because we didn't trust really the values at the end of the experiment, because at the end of the experiment, the angiogenesis take place, and so on, which is not included in our model. Okay, and then we got so for 6 grays and 24 grays, we find the delay and the corresponding probability values. And of course, for those 0, we had 0 delay, and we fit functions. So then we've got the response of a cell to a single dose. And here's maybe just mention here that we've got, here is the comparison of simulations. So it's the colors, and the markers like squares and triangles are the data from Kelly et al. Paper. And about others, you can check JTB paper. Okay, but what about the multi-dose irradiation? So to do that, we focus on Otsuka and Tsuji papers, and actually it's a one group from Japan. So they performed 18 external experiments, and I was very happy to find them in the literature. And we've got one control parameter to fit, and one objective function, and maybe only single short remarks that damage, DNA damage are linear in dose, so there's a linear dependence. And not all breaks are repaired in a long run, and reciprocal repair function fits better experiments than others. So we follow that idea. And so what's this reciprocal repair model or function? It's the formula given in this rectangular, so what's the issue with these multi-doses? So the problem is that whenever a cell receives a dose, then it starts to repair, and if it gets another dose after a short time after the first one, it doesn't mean that it's the same as to give a double dose to the cell, because it's already managed to repair DNA at some part. So then you've got another one, and then there is like the partial repair, and another one, and another one. So the effective dose is like this cumulative dose, which takes into account that the cells managed to repair DNA for some time. And we follow the repair model, which assumes that the damaged sites, repair is given by this formula. So it's quite easy one, and the only unknown parameter is half time of repair. And it was tested or investigated for several cell lines, and we found that pig skin cells got this half time repair equal to 0.67 hours, and for example, rat foot cells 4 and 2 hours. And we needed to estimate that parameter as well. But Suji and Otsuka, or they perform 18 excellent experiments we can base on. So first, in Suji 2006 paper, authors reported experiments when they use 2 fractions of 10 grays given in different time intervals. So it's like this, that part. And then a few years later, 4-hour delay was fixed, and they were given different fractions with different amount of irradiation. So to estimate our tau value, we replicate all that experiments. And so we tested 18 different values of tau, and for 18 different experiments, and each experiment was run on 10 tumors. So maybe I didn't make it clear, but our study was performed on 10 similar but a little bit different tumors. And the result of the simulation is given here. So we've got this effective dose and for different tau values. And here is the outcome of Otsuka et al. Experiments, biological experiments. So we use mean square error and try to find the tau such that our error function is small, the smallest. So it was 0.8 hour. Okay, so now about the protocols. So how we represent the protocols. So we might represent them in different ways, but we represent them as a vector which consists of small vectors. So each small vector got the dose at first coordinate and the time from the previous to the current dose. So in case of the first dose is time from 0 from the beginning of the experiment till the first dose. And then we've got second dose and time between the first and the second dose and so on. So it's a possible representation of our protocols. And here we've got this benchmark results I mentioned before. So it's nothing new, but just we present here the normalized cell account for benchmark 1 and benchmark 2. And now the study, our first approach from +1 paper when we use a genetic algorithm. So again, it's a computational procedure, I would say, which allow us to construct new protocols from the existing ones. So the idea is that we have some constraints on protocols. So we assume that the protocol maximal duration time is 5 days and the total dose is 10 grays. And we've got the initial pool of protocols. And then we use different operators, different types of selections. So top 1 means that we choose the best protocol. Top 5, it means that we choose the best 5 protocols. 10% of best protocols, and tournament means that we choose 2 protocols and run the tournament between them. Then we pass the the parents protocols to the crossover operator. And here's the representation of parent 1 and parent 2 protocol. And we choose the crossover point, and then we exchange the parts of genome between parents, and we've got a child protocol. Of course, we've got another one which starts with the red and in the front and green at the end. And then we test the protocol. So we've got our model, and then we get fitness of the protocol. We put it to the library, and we repeat it and repeat it and repeat it. Okay, so a few words about the fitness score, how we done it. So we compare normalized cell count for the benchmark and from the tested protocols, multiply them by 100, and we apply penalty if the protocol is new protocol is worse than the benchmark protocol, and so that we get the performance. So the upper index stands for the tumor number, because as you remember, I said that we test 10 different tumors. And then we run statistical one-tail test, t-test, when the hypothesis null, zero, H0 hypothesis is that this performance is the worst, and the idea is that we want to reject the H0 hypothesis, making very small error, which is reported by the p-value. So if we've got two candidates, then better candidates got the smaller p. Okay, and here's the outcome. So after 40,000 CPU hours, we get best protocols, and the dose was fixed as in the benchmarks, and we get average improvement of 9.4% for the benchmark 1, and for benchmark 2 4.1. And what we observe is that we see some kind of synchronization of the cells. And then we choose like 100 protocols and look at the density time gaps between the different doses, and we observe some kind of peaks. So that encourages us to run handmade protocols, synchronic protocols, and test them against the benchmark 1 and benchmark 2. So for example, in case of benchmark 1, regular, I will say, periodic protocol of with the gaps of 17 hours give the same improvement results, but with lower p-value, and also the range is lower, which means that actually it's a better protocol than the one found by genetic algorithm. Okay, so as the summary of what I just said, and now I would like to say a few words about our recent work. So it was we allow not only change the timing between doses, but also the amount of irradiation applied to the tumor. So, general restrictions are the same as before. So the total dose it's smaller or equal to 10 grays, and we still focus on the 5-day protocols. And if you use the previous approach, so single dose fixed approach, then we've got quite large space of protocols. I mean, I didn't put here all the restrictions on timing, but we've got something like 10 to the power of 11 protocols. And in case of BM2, we've got 10 to the power of 6. But if we switch to multi-dose delay approach, so when the dose is not fixed, and the dose can be from the set of 0.25 till D max, which is given for the particular experiment. and we assume that the minimal delay between doses can be 6 hours, then we can give 20 fractions over 5 days. And if we only think that we can take the Dmax equal 5 grays, we got 10 to the power of 15 possible protocols. So it's a vast space of possible protocols. And we somehow restricted adding additional constraints. So for each experiment, we define the maximal single dose value. It means that at single time point, only the dose equal or smaller than the given Dmax is applied. For each experiment, we settle the minimum delay between the doses. And the minimal time step is equal to 30 minutes, and I would say dose step, it's 0.25 grays. And everything wouldn't be possible if we wouldn't work hard on code of a model. So the original model was already parallelized using MATLAB environment, but it was still a little bit slow. Like one experiment on one tumor 10-day experiment took like 70 minutes run on cluster. I asked students to rewrite the original MATLAB code to intermediate version. It was C++ implementation. And later on, one of the students said, okay, I can do it better. And he rewrote the GPU implementation, delivering more than 700 speed up of the code execution comparing to the original parallelized MATLAB code. And we also needed to have access to infrastructure. So for this +1 paper experiments, we used a massive facility. So actually it was not designed to run MATLAB simulations, but they were very helpful, and they installed MATLAB and with all these packages. And for the C++ and GPU implementation, we use RISE and Topola clusters provided by ICM, so Interdisciplinary Center of Mathematical and Computer Modeling of Warsaw University. And if you are interested, here are the parameters of the servers we used. And first of all, we needed to check if this CPU and GPU implementations are good enough, I mean, close to each other. So here in panel A, you see the relative deviation from the median, and CPU stands for, I mean, the blue bars are stand for CPU, and orange one for GPU. And here are the 60 protocols evaluated on the same 10 tumors. And for the CPU, each protocol was evaluated 48 times on each tumor. And in case of GPU, we ran 100 iteration on each tumor. The difference is because, I mean, CPU are much faster than, I mean, GPU is much faster than CPU. So it's only for the comparison. And you see that actually Okay, and the protocols were random protocols, and only restriction was that all of them had a total dose smaller than 10 grays, and each took not longer than 5 days. And so I think we are quite good with it. There are some small exceptions. And to test them rigorously, we ran two-side t-test. And on panel B, we report the p-value for that experiment. And we also tested the normality of the distribution received from GPU experiments. And on panel D, you've got an example of such a distribution and the corresponding normal distribution with the same parameters. Okay, so but there were some things that were different corresponding to the previous approach. So now we use, I think, easier, simplest fitness function, which is simply the difference between the number of all occupied sites minus the actually occupied sites. So the bigger fitness function is, the better protocol is. And we also measure the suppression improvement, and it's like, I think it's a quite standard way. So we took the average number of occupied sites after testing e-protocol on 10 tumors, and average number of occupied sites for a reference protocol. So a benchmark on benchmark throughout other benchmark, and divided by this average number of occupied sites for the reference protocol. And also our approach to genetic algorithm was different. So now we start with the generation of 40 protocols, and immediately we copy 4 best protocols to the next generation. And for the all 40 protocols in generation T, we apply a selection operator. And in case of this approach, we use 3 different selection operators: roulette, simple, and tournament. Then in this way, we select 16 parent protocols and push them to the crossover and mutation operators. And we use 3 different crossover operators and 4 different mutation operators. So we use 1-point crossover like in the previous approach, but we also use 2 points crossover operator or normalized crossover and mutation. So it's easy to guess that because now we change timing and the dose, so we can mutate the time of a dose, size of a dose. We can sweep 2 different events, or we can split the dose, randomly selected dose into 2 different. So we apply this all these operators till we get 36 child protocols. We evaluate them, and we got the new generation. And we run this 100 times. So I didn't want to present the tables, but I think that one good picture is better than 3 or 4 tables. So we've got the comparison of the results for the clinical protocols. BM1, so when the dose was fixed and was 1.25 grays. BM2, when the dose was fixed, the dose was fixed for BM clinical protocol, and it was to grays, and in this paper, when we've got a fractional dose over 2 grays, but small or equal to 4.5. So the state of art is our previous finding from +1 paper. So when the dose was fixed according to BM1 or BM2, and this paper, it's dose is assumed that it's not greater than 1.25, and we play also, so we play with single dose and timing between doses. The best protocols we get for this setup gain like 4% comparing to the previous approach, and 9.1% comparing to the original clinical protocols. And for the BM2, so for the benchmark when we had 2 grays, we get improvement of 4.5% comparing to the previous approach, and 8.2 comparing to the clinical used protocols. And it's natural when we increase the fractional, single fractional dose over 2 grays, we get better results. But still, for all these protocols, the total dose given during the protocol, it's lower or equal to 10 grays. So the best of the best protocols is the one when we assume that the total, the single dose, it's not greater than 4 grays. And as you see, it's like, it looks like that there is some kind of switch in timing. So this protocol waits for some time to apply the dose, but it's not the case that the dose is given at the very end of the protocol. And what we then we look on this 10 best protocols for each setup we considered, and plot some kind of density function when we've got the delay on x-axis, and we've got fraction or size of dose, single dose, and we observe some, there are 2 peaks, 15.5, so it's timing, and the dose is 1.4, and here is opposite, and here is another peak, 0.5 and 0.7. And that made us to consider handmade protocols. And the handmade protocols are the, I would say, dummy protocols when we choose the values from the peak and repeat it as many times as we can till we reach the restriction for the total dose. And the second handmade protocol is the same as the previous one, but on the first dose we use the values from the smaller peak. And in the third one we use, it's the same as previous, but we also change the dose at the end. And the last one, handmade protocol, is very, we just divided divide the total dose and timing such that we can get to get as close to the 10 grays as possible. And then we run the evaluation of the protocols, and it appears that actually this the last one is the best one among these handmade protocols, and it's comparable with the best found by genetic algorithm under assumption that we apply 1.25 grays protocol. So if I've got time, so some discussion and conclusions. So I think that it's very important to to have access to the good in vivo and in vitro data for the calibration and validation of models. And actually, there is not so many high fidelity computational models, but I think that due to the fact that we observe the reducing computational cost, it should appear more and more such models. Our model can be adjusted to any cell line we want. The only condition is that we need to have sufficient input data and parameters for our model or experiments to calibrate the model. And what we want to do in the future, so it would be great if we could test our synchronization periodicity founding in a lab. So actually we contacted the Japanese team, but they never reply. I mean, we try to. We would like to focus on applicability of protocols. So yes, so okay, we can find very good protocols theoretically, but then we also need to take into account that someone needs to apply them in a reality. So perhaps like, I don't know, 17 hours protocol with a gap of 17 hours, not the best solution, because every day you've got the different time when you need to appear to receive the treatment. So actually what we think is that we supposed to add another restrictions when we are trying to find the best protocols using genetic algorithms. And there is another option that we can use machine learning approach. So we've got already some preliminary study in that direction, reinforcement learning, and we are already able to replicate the more or less the obtained results with the results we obtain with genetic algorithms. And the natural thing is to extend the model, so include other factors like vascularization of tumors and stuff like that, and also, of course, to model larger tumors than we considered. So few words about the collaborators. So about Simon Angus, I already told you a few words. So the recent work was done thanks to collaboration with Wojtek Ozimek. So he works right now at the Ardigan company, but he was a master student at Jagiellonian University. Rafał Banaś now works in NVIDIA. So he was responsible for rewriting code for GPU. And Paweł Gora, he is a PhD candidate at the University of Warsaw in computer science. And the C++ code implementation was done by Rafał Banaś, Julia, Olaf, and Agnieszka. So they were bachelor students at computer science at Warsaw University. And of course, the acknowledgements. So it's clear that this work was supported during all these years by different grants. So there was some kind of support from Polish Ministry of Science. I get a visitor research grant to visit Monash University. There was also, at some point, we done some part of work in the framework of National Science Center program And I also wanted to acknowledge the support of Massive and ICM, which gave us opportunity to run all that all that numerical models. And here's the summary. So about our work and about source files, and you can download the code and it's publicly available. And yeah, and that's all. Thank you for your attention, and I will be happy to answer any questions.
Thank you very much, Monica. Are there any questions? I do have a couple of questions. The first one would be, you mentioned toward the end of the talk the idea of including vessels in your model, and then I assume blood flow and so. How that could be done?
Yeah, so actually right now we've got, we model a vascular tumor growth, and all the experiments run by Japanese team was also on that kind of tumors. And so it is, because now we've got this quite fast code, and we can really include the normal tissue and vessels in a model as well. So it's like a next step, which also means that we need to evaluate and calibrate the model once again.
Okay, and the second question is, you have a number of free parameters that then you recover from the literature, and I assume some of them come from some types of cancer and some others from other types. Yeah, that's exactly what I mean.
Okay, so yeah, so we've got a lot of parameters, and that's why we focus on the particular cell line and particular experiments run by particular groups, so that we really follow the same cell line. So it's like, I guess it's like 34 plus parameters only to model the tumor growth.
But they are all from the same cell line?
Yeah.
Is that so? Okay, okay.
I mean, only few of them are estimated, like the glucose.
So in a sense, you expect your results to be robust for that cell line. Is that correct?
Yeah,
okay.
Yeah, and we also to ensure that it's not like lucky guess when we look on the best protocols. We all the protocols are evaluated several times over 10 different tumors. I mean, very similar because they are grow from the same seed at the beginning, but because it's stochastic, so each tumor is a little bit different.
Okay, yeah, makes perfect sense. Thank you. Any questions from the online side? No? Then I think we can stop here and thank Monica again for the nice talk.
Thank you.
Okay, I think we can also stop here and reconvene tomorrow morning at 9:30. Have a good evening.